a planet crosses in front of its star. For a few hours, a tiny fraction of starlight passes through the atmosphere of that distant world. That starlight travels 124 light-years to reach us. Inside that faint light, there are secrets. The James Webb Space Telescope, a golden honeycomb adrift 1 million miles from Earth, captures this light. It splits the ancient photons into a rainbow of colors. Each chemical floating in that alien atmosphere absorbs specific wavelengths of the starlight. It is a process that leaves a unique and telltale fingerprint. Methane greedily eats up certain shades of red. Carbon dioxide swallows a particular band of infrared. Water vapor leaves its own distinct and jagged signature. Scientists call this transmission spectroscopy, and it works like reading a barcode written in the light of a distant sundae. This technique is confirmed science. It has been used successfully on dozens of other worlds. When the planet, a world we call a Hycean, transits its star, Webb detects the subtle drop in brightness. But more importantly, it catches the chemical fingerprints left behind by every molecule floating in that alien sky. The process is one of almost unimaginable precision. The telescope sits far beyond our own blurring atmosphere where nothing can interfere with its pristine view. Its mirrors, coated in a thin layer of pure gold, are designed to capture the faint warmth of infrared light. These are the wavelengths where the molecular signatures of life shine the brightest. Here is what makes this instrument so revolutionary. Webb can detect the presence of chemicals at concentrations as low as parts per million. On Earth, that would be like finding a single drop of ink that has been dissolved in an entire swimming pool. The data from the telescope arrives not as a picture, but as a graph. It is a jagged line that shows the dips and peaks at specific wavelengths of light. Each one of those dips represents a particular molecule that has absorbed the starlight. If you can match the pattern of the dips, you can identify the chemical. Methane, for example, has 4 characteristic absorption bands that it carves out of the light. Carbon dioxide shows 2 strong and unmistakable features. Water leaves behind 3 distinct and jagged marks. The James Webb Space Telescope uses 2 different instruments for this painstaking work. One is called the Near-Infrared Spectrograph, or NIRSpec. It looks at the wavelengths of light that are between 0.6 and 5.3 microns. The other is the Mid-Infrared Instrument, or MIRI, which examines the wavelengths from 5 to 28 microns. Together, they are able to create a complete and overlapping picture of what chemicals are floating in the distant atmospheres. When scientists aimed Webb at this particular ocean world, they had expected to see methane and carbon dioxide. Both of these gases had been detected before by using the Hubble Space Telescope, but the older instrument had struggled with the precision of its measurements. What they found instead made them check their instruments 3 separate times. Dr. Evelyn Reed stared at the graph on her screen, her coffee growing cold beside her. The data had been processing for days, filtering out the overwhelming glare of the parent star. Evelyn was a veteran of the exoplanet game, a field where 99% of the work was eliminating false positives. She had seen phantom signals come and go with the changing temperature of a sensor. She had seen cosmic rays masquerade as distant worlds. But this was different. This felt solid. Her algorithm, a sophisticated piece of artificial intelligence she had affectionately named Kepler's Ghost, had flagged it. It was a series of absorption features that matched only one thing in its vast chemical library. The molecule was dimethyl sulfide, or possibly its very close chemical cousin, dimethyl disulfide. Both of these molecules share very similar spectral signatures in the observed range of light. The signal had appeared at the wavelengths between 4 and 5.2 microns. Multiple absorption bands had lined up perfectly with the laboratory measurements of these sulfur compounds. The sheer strength of the signal had indicated concentrations that were exceeding 10 parts per million. For a moment of reference, the atmosphere of the Earth contains these very same molecules at a concentration of less than 1 part per billion. Something on this distant world was producing them at a rate that was thousands of times higher than what we see here on our own planet. But what was coming next was even stranger. The scientists on her team had run the observations twice. They had used 2 different instruments to be absolutely certain. Both times the exact same signature had appeared. The probability that this had occurred by random chance was sitting at just 0.3%. That is what is known in statistical terms as a 3 sigma level of certainty. It is not quite enough to be able to declare a victory, but it is far beyond a simple coincidence. To be able to reach 5 sigma, which is the gold standard for any scientific discovery, they would need just 2 or 3 more observation windows. Those could happen within the next year. The next question becomes an obvious and a heavy one. What could possibly be creating these molecules in such staggering and unimaginable amounts? On our own planet, dimethyl sulfide has only one confirmed and undeniable source. That source is life. Specifically, it comes from the tiny organisms that are floating in our oceans, which are known as phytoplankton. These microscopic algae are producing a compound that is called dimethyl sulfonopropionate as they are growing. When they die or when the bacteria are breaking them down, this compound is transformed into dimethyl sulfide. The gas then escapes into the atmosphere and you can smell it. If you have ever walked along a beach and you have noticed that sharp, slightly unpleasant scent in the air that is dimethyl sulfide, scientists have searched for decades for any non-biological way to be able to make this molecule in the atmospheres of planets. They have found nothing that is able to work at any meaningful scales. Laboratory experiments can create some trace amounts of it through the reactions that are between methane and hydrogen sulfide under some very specific conditions. But these chemical pathways are incredibly inefficient. They require exact ratios of ingredients, and they produce dimethyl sulfide at concentrations far below what we can observe on Earth, let alone what the Webb telescope detected on this distant world. Here is why this particular molecule matters so much. Most of the other potential biosignature gases have some problems. Methane can be coming from volcanoes. Oxygen can be being created when the ultraviolet light from a star is splitting water molecules. Phosphine might be forming in the violent storms on the gas giants. Each of these has at least one known abiotic pathway that is able to muddy the interpretation. But dimethyl sulfide and its cousin dimethyl disulfide stand apart from the rest. Their chemistry requires some specific biological pathways that no known geological process is able to replicate at such high concentrations. The molecule also has a very short lifetime. In the atmosphere of the Earth, dimethyl sulfide breaks down within a matter of days. The sunlight tears it apart. The oxygen in the air attacks it. The hydroxyl radicals in the atmosphere destroy it. This means that any dimethyl sulfide that we are able to detect must be being continuously replenished. On the Earth, the phytoplankton are blooming and are dying in cycles, and they are pumping a fresh supply of the gas into the air. The very fact that we are able to measure it at all is proving that something is making it constantly. Now imagine finding this very same gas on another world and at a concentration that is 10,000 times higher than that of the Earth. The math becomes almost unavoidable. Whatever source exists on that world, it must be incredibly powerful. Some process is generating either dimethyl sulfide or dimethyl disulfide much faster than the chemistry of the atmosphere can destroy it. On the Earth, our oceans are teeming with trillions upon trillions of phytoplankton that are working around the clock. To be able to produce the concentrations that the Webb telescope had detected would require a form of life on a scale that is difficult to even comprehend. The theoretical work that had been published before the observations from the Webb telescope had predicted this exact scenario. Scientists who had been modeling some hypothetical ocean worlds with hydrogen atmospheres had calculated that If life were to exist there, then the dimethyl sulfide would be accumulating to much higher levels than it does on the Earth. The hydrogen atmosphere would be slowing down the destruction pathways for the molecule. The microbes could be thriving in the warm oceans that were beneath. Their waste products would then build up over a long period of time. The predictions had matched the observations almost perfectly. This is a theory that is being supported by the models, but it is not yet a confirmed fact. But the alignment between the prediction and the observation is what is making the scientists cautiously optimistic. One of the researchers at Cambridge had stated that given everything that is known about this planet, an ocean world that is teeming with life is representing the scenario that best fits the data. But caution is still remaining the watchword. The next step will involve ruling out every single alternative explanation, no matter how unlikely it might seem. What if something else, something that we have never even considered, could be making these molecules? When the scientists are saying that they have a 99.7% level of confidence, they are talking about the field of statistics. Specifically, they are meaning that the signal that they have detected has only a 0.3% chance of being just random noise. In the language of statistics, this is what is known as a 3 sigma level of certainty. Picture flipping a coin. If you get 10 heads in a row, then you might begin to suspect that the coin is weighted. That is roughly a 3 sigma event. If you get 20 heads in a row, then you would be absolutely certain. That is a 5 sigma event. The gold standard for claiming a scientific discovery is sitting at 5 sigma. At that particular level, the probability of an error is dropping to below 0.00006%. Particle physicists had used the 5 sigma standard when they had announced the discovery of the Higgs boson. Astronomers had used it when they had confirmed the existence of gravitational waves. For something that is as profound as detecting the existence of alien life, nothing less will suffice. Right now, this discovery is sitting at a level of 3 sigma. It is exciting, but it is not yet conclusive. Here is how they had calculated this number. The James Webb Space Telescope had collected the data that was showing the absorption features at some specific wavelengths. The scientists had then compared this data against their models. One of the models had assumed that either dimethyl sulfide or dimethyl disulfide was present in the atmosphere. Another model had assumed that these molecules were completely absent. The model that had included the sulfur compounds was a significantly better fit for the data. The statistical tests had then revealed that the probability of getting such a good fit, just by chance, if the molecules were not actually there, was equal to 0.3%. But chance is not the only concern. Systematic errors can also be fooling the instruments. Maybe the calibration of the telescope had drifted slightly. Maybe the thermal noise in the detectors had created some false signals. Maybe the star itself has some unusual properties that are mimicking the signature of dimethyl sulfide. The scientists had spent months checking for all of these possibilities. They had used 2 different instruments on the Webb telescope. Both of them had seen the same signal. They had examined the observations of other planets to be able to ensure that the signature was a unique one. They had modeled dozens of different alternative atmospheric compositions. Nothing else had been able to fit the data as well. To be able to reach the 5 sigma level, they are needing more data. Each of the observation windows is lasting for about 8 hours as the planet is crossing its star. They have used 2 of these windows so far. The scientists are estimating that they will need 2 or 3 more. That means another 16 to 24 hours of time on the telescope, and it will be spread out across multiple different transits. The planet is completing an orbit every 33 days, so the opportunities are arising quite frequently. But the Webb telescope is the most oversubscribed telescope in all of history. Thousands of different astronomers are competing for time on it. Getting an approval for the observation time requires a very rigorous selection process. The lead researcher has stated that they have formally applied for some additional observation time. A review panel will now have to decide whether the science is justifying the cost. If they are approved, then a confirmation could be coming within the next 12 months. That timeline is putting us potentially just 1 year away from knowing whether we have detected the existence of alien life. 1 year away from being able to answer humanity's oldest and most profound question, are we alone? But here is what is making this particular moment so electric. Even at a level of 3 sigma, and even with the uncertainty that is remaining, we have now crossed a new threshold. For the very first time in all of human history, we have the data from another world that is easier to be explained with the presence of life than it is without it. That has never happened before. What is it that is making this particular world special enough to be able to produce such a signal? The planet is orbiting a star that is known as a red dwarf. These stars are smaller, cooler, and dimmer than our own Sun. This particular red dwarf has a temperature of about 3,184 degrees Celsius. Our own Sun is burning at a temperature of 5,500 degrees. The red dwarf is containing only 45% of the radius of our own Sunday. It has less mass, less heat, and less light. But here is the trick. The planet is orbiting much closer to its star to be able to compensate for this. The Earth is sitting at a distance of 93 million miles from our own Sunday. This ocean world is orbiting at a distance of just 13 million miles from its star. That is putting it 167 times closer than the Earth is relative to the size of its star. This distance matters more than you might think. The intensity of the starlight is following the inverse square law. If you double your distance, then you will receive 1/4 of the light. If you move 10 times closer, then you will get 100 times more light. This planet is orbiting so close that despite the dimness of its star, it is receiving roughly the same amount of energy that the Earth does. Scientists are calling this the habitable zone. It is the region that is around any star where a planet that has the right kind of atmosphere could be able to maintain the liquid water on its surface. For our own Sun, that zone is spanning from about 90 million to about 140 million miles. For the red dwarfs, the habitable zone is sitting much closer in, and it is sometimes just a few million miles out. This has been confirmed by decades of observations and climate modeling. The temperature is not just about the distance. The atmospheres are changing everything. A planet that has a thick atmosphere is able to trap the heat through the greenhouse effect. Carbon dioxide and methane are particularly good at this. Water vapor is helping too. The right mix of these gases can be keeping a world warm even if it is far from its star. Venus is demonstrating this principle when it has gone wrong. Despite being closer to the Sun than the Earth Venus would actually be cooler if it were not for its crushing carbon dioxide atmosphere. Instead, the surface temperatures on Venus are reaching 470 degrees Celsius. This ocean world has a hydrogen-rich atmosphere. Hydrogen is less efficient at trapping the heat than carbon dioxide is, but it is making up for this with its sheer volume. The models are suggesting that the atmosphere might be representing up to 6% of the total mass of the planet. For a point of comparison, the atmosphere of the Earth is less than 1/1,000,000th of the mass of our own planet. That much hydrogen is creating a very strong greenhouse effect, even with its lower efficiency per molecule. But here is where a complication is coming in. The same closeness that is allowing for the liquid water is also bringing some danger. The red dwarfs are violent stars. They are producing some powerful flares, which are the sudden bursts of radiation and the charged particles that are blasting the nearby planets. These flares can be stripping away the atmospheres over the course of millions of years. They are bathing the planets in the ultraviolet and the X-ray radiation that is destroying the complex molecules and is sterilizing the surfaces. Yet this world appears to have been able to retain its atmosphere. The observations are showing an abundance of hydrogen, methane, and carbon dioxide. If the star were to be constantly stripping the atmosphere away, then we would be seeing some signs of the atmospheric loss. The presence of the heavy molecules is suggesting that the planet has been able to hold on to its envelope for a long period of time. Perhaps its strong gravity is helping. Perhaps the atmosphere is thick enough to be able to weather the storms, or perhaps we are just witnessing something that is very special, a planet that is in a brief window of time before its atmosphere is disappearing. The star itself is being estimated to be about 2.4 billion years old. The Earth is 4.5 billion years old. This star system is roughly half of our own age. It is young enough that the planet may still be geologically active, and it is old enough that any life that might exist there would have had the time to be able to evolve. What is happening when you are combining all of these factors with the strangest feature of this world? One single orbit is taking just 33 Earth days. That means that a year there is lasting for just over a month. Imagine celebrating your birthday 33 times faster. You would be over 1,000 years old by the time that you had reached your 30th birthday by the standards of the Earth. But this speed is having some consequences that are rippling through every single aspect of the planet's behavior. First, let's consider the seasons. On the Earth, the seasons are occurring because our axis is tilting at an angle of 23 degrees. When the northern hemisphere is tilting toward the sun, we are getting the summer. 6 months later, we are tilting away and we are getting the winter. This ocean world is likely to be having a minimal axial tilt, which is meaning that the seasons would not be happening in the way that we are experiencing them. Instead, any variation in the climate would be coming from the orbit itself. And here is where things are getting interesting. The orbit is not a perfectly circular one. Scientists are measuring this by using a number that is known as the eccentricity. The orbit of the Earth has an eccentricity of 0.017, which is nearly a perfect circle. This ocean world has an eccentricity of about 0.09, which is over 5 times more elliptical. This has been confirmed through some very precise measurements of the timing of the orbit. That is meaning that the distance from the star is changing significantly throughout each and every orbit. At the closest point, the planet is sitting about 12% nearer to its star than it is at the farthest point. That might not be sounding like a great deal, but the inverse square law is amplifying this difference. The planet is receiving about 43% more starlight at its closest approach compared to its farthest distance. Imagine if the climate of the Earth were to be swinging that wildly. Every few weeks, the temperatures would be spiking and then crashing in the cycles. Any water that was on the surface would be facing the constant freeze-thaw cycles. This is creating a problem for the stability. Life as we are knowing it is requiring some stable temperatures. The extreme swings are making it very hard for the complex chemistry to be able to establish itself. The water might be freezing at one part of the orbit, and then it might be boiling at another. The organisms would be needing to be able to survive both of these extremes within a single month. On the Earth, the extremophile bacteria are able to handle the wide ranges of temperature. Some of them are thriving in the boiling hot springs. Others are surviving in the Antarctic ice. But asking the organisms to be able to handle both of these extremes on a monthly schedule is a different kind of a challenge. Yet, the signal of the dimethyl sulfide is persisting. If life is existing there, then it has been able to adapt to this chaotic rhythm. Perhaps the thick hydrogen atmosphere is acting as a kind of buffer, and it is smoothing out the extremes of the temperature. Perhaps the life is retreating to the deeper waters during the temperature swings, and it is waiting for the conditions to be stabilizing. Perhaps the oceans themselves are storing enough of the heat to be able to prevent the wild fluctuations. There is another problem that is with the fast orbits. When a planet is orbiting this close to its star, the gravitational forces are becoming very intense. The star is pulling harder on the near side of the planet than it is on the far side. Over the millions of the years, this difference in the pull is creating the tidal forces that are slowing down the rotation of the planet. Eventually, the planet is becoming tidally locked. One side of it is always facing the star, and it is in a permanent daylight. The other side is facing away, and it is in an eternal darkness. Scientists are suspecting that this ocean world is tidally locked, though this is remaining unconfirmed. If this is true, then the day side would be scorching hot. the night side would be frozen solid. Only a narrow twilight band that is between the two hemispheres might be being able to maintain the temperatures that are suitable for the liquid water. The wind would be howling across this boundary, as the hot air from the day side would be rushing to be filling the frigid night side. The weather patterns would be unlike anything that we are seeing on the Earth. But what if the thick hydrogen atmosphere is changing the game? The computer models are showing that a dense atmosphere can be transporting the heat from the day side to the night side very efficiently. This could be creating some more habitable conditions across the larger portions of the surface. Without being able to see the planet directly, the scientists can only be estimating these effects. What they are knowing for certain is that this world is nothing like the Earth in the terms of its daylight cycles. How is a planet that is 2.5 times the size of the Earth being able to maintain the conditions that might be supporting life? The planet is having a radius that is 2.6 times larger than that of the Earth. That is making it massive. Its volume is over 17 times that of our own. If you could be standing on the surface, and you were to be assuming that there is a surface, then the gravity would be crushing you at about 2.5 times the strength of that of the Earth. Every single step would be feeling like you were carrying another copy of yourself on your own back. This has been being confirmed through the precise measurements of the mass and the size of the planet which have been being derived from the orbital mechanics. But the size is creating a problem. The planets that are this large are usually not looking like the Earth. They are looking like Neptune. Our own solar system has the 4 rocky planets and the 4 gas giants with nothing that is in between. This ocean world is sitting exactly in that gap. Scientists are calling the planets like this the sub-Neptunes. They are bigger than the Earth, but they are smaller than Neptune. We've discovered thousands of them that are around the other stars, but we are having none in our own system to be studying up close. Here is the mystery. We are not knowing what the sub-Neptunes are made of. Are they the rocky planets that have been capturing the huge atmospheres? Are they the icy worlds like Neptune that have never been growing large enough to be becoming the full gas giants? Are they something else entirely? A type of the planet that is not existing in our own solar system? The answer is, what is determining whether the life could be surviving there? The density is offering the clues. The Earth is having a density of 5.5 grams per cubic centimeter. That is because we are mostly being made of the iron and the rock. Neptune is having a density of 1.6 grams per cubic centimeter. That is because Neptune is mostly being made of the water, the ammonia, and the methane ices that are being wrapped in the hydrogen and the helium gas. This ocean world is having a density of 2.67 grams per cubic centimeter, and it is right between the Earth and Neptune. One of the possibilities is this. The planet is having a rocky core that is perhaps being 3 to 4 times the mass of the Earth. Above that is sitting a mantle of the high-pressure ice. This is not the ice that you are finding in your own freezer, but the ice that is forming under the extreme pressure and is staying solid even at the high temperatures. Above that might be being the liquid water, and above that might be being a thick atmosphere of the hydrogen and the helium. This structure is purely theoretical. It is a model that has been being built from the measurements of the mass and the density. No one is knowing for sure. This model is leading to the concept of the Hycean worlds. The word is combining the hydrogen and the ocean. The idea is suggesting that the planets with the hydrogen atmospheres and the liquid water surfaces could be being habitable despite being much larger than the Earth. The hydrogen atmosphere would be trapping the heat through the greenhouse warming. The liquid water would be providing a medium for the life. The microbes could be floating in these oceans just like the phytoplankton are floating in the seas of the Earth. But the critics are pointing out the problems with this picture. At the surface, pressures that are being expected on such a large planet, the water might not be staying liquid. It might be existing in a supercritical state where the distinction that is between the liquid and the gas is breaking down. Imagine the water that is flowing like the liquid, but it is having the density of the steam. That state is beginning above 374 degrees Celsius and above 221 times the atmospheric pressure of the Earth. If the surface temperature or the pressure is exceeding these thresholds, then the liquid oceans cannot be existing. Some of the scientists are arguing that this world is too hot. The climate models are suggesting that with its thick hydrogen atmosphere and the amount of the starlight that it is receiving, the surface temperatures could be exceeding 500 degrees Celsius. At that temperature, any water would be existing as the supercritical fluid or the steam. The surface might be being the molten rock, and it might be being a magma ocean that is being wrapped in a hydrogen blanket. If so, then the signal of the dimethyl sulfide is needing a different explanation. But the other models are telling a different story. They are suggesting that if the clouds are forming in the upper atmosphere, then those clouds could be reflecting enough of the starlight to be keeping the surface cool. An albedo, which is the measure of the reflectivity that is above 90%, could be maintaining the liquid water. Whether such clouds can be forming is remaining uncertain. The chemistry of the hydrogen-rich atmospheres is making the formation of the clouds different than it is on the Earth. What is making the absence of the certain molecules a crucial clue? The oceans of the Earth are containing about 25 trillion of the phytoplankton. These microscopic organisms are drifting in the sunlit surface waters, and they are using the photosynthesis to be turning the carbon dioxide and the sunlight into the energy. They are producing roughly half of the oxygen that we are breathing. They are forming the base of the oceanic food chain, and they are making the dimethyl sulfide. When you are visiting the beach, that distinctive smell that is in the air is coming largely from these tiny beings. The phytoplankton are creating a compound that is called dimethyl sulfoniopropanate to be regulating the salt balance in their cells. It is acting as an osmolyte, and it is helping them to be dealing with the saltiness of the seawater. When the phytoplankton are dying, or when the bacteria are attacking them, the enzymes are breaking down this compound. One of the breakdown products is the dimethyl sulfide. The gas is escaping into the atmosphere at a rate of about 100 million tons per year globally. This is the confirmed science, and it has been being measured directly through the atmospheric sampling and the satellite observations. The molecule is not lasting for long. The hydroxyl radicals in the atmosphere are attacking it within the days. The sunlight is breaking it apart. It is oxidizing into the sulfur dioxide and then into the sulfuric acid, which is forming the tiny particles. These particles are seeding the clouds. More of the clouds is meaning more of the sunlight that is being reflected back to the space, and it is cooling the planet. Some of the scientists are proposing that this is creating a feedback loop. The warmer oceans are producing more of the phytoplankton. More of the phytoplankton are making more of the dimethyl sulfide. More of the dimethyl sulfide is creating more of the clouds, and more of the clouds are cooling the planet. This hypothesis is remaining unproven, but it is being widely discussed. Now let's consider what it is meaning to be detecting the dimethyl sulfide on another world. The signal is requiring the continuous production. Something must be churning out the molecule faster than the chemistry is destroying it. On the Earth, the combined efforts of the trillions upon trillions of the phytoplankton cells are barely maintaining the atmospheric concentrations of 1 part per billion. To be reaching 10 parts per million, which is the concentration that has been being observed on this ocean world, is requiring a production rate that is 10,000 times higher. What could possibly be doing that? One of the options is simply more of the phytoplankton. If the oceans there are containing vastly more of the microbial life per unit of the volume than the oceans of the Earth are, then the math is working. But why would that be? Perhaps the combination of the hydrogen atmosphere and the liquid water is creating the ideal conditions for the microbial blooms. Perhaps the nutrients are more abundant. Perhaps the lack of the predators is allowing the populations to be exploding unchecked. Another of the options is involving the different chemistry. Perhaps the organisms there are producing the dimethyl sulfide directly rather than as a byproduct. On the Earth, the phytoplankton are making the dimethyl sulfonopropionate for one reason, and the dimethyl sulfide is happening as a side effect. On another world, the life might be using the dimethyl sulfide as a signaling molecule, a metabolic product, or even a waste product of the energy generation. The different evolutionary pressures could be leading to the different uses for the same molecule. There is also the question of the bacterial contribution. On the Earth, the bacteria are playing a huge role in converting the dimethyl sulfonopropionate into the dimethyl sulfide. The certain bacterial species are specializing in this transformation. An ocean that was full of these bacteria that were feasting on the organic matter could be producing the enormous quantities. The dimethyl disulfide that has been being detected alongside the dimethyl sulfide is supporting this. On the Earth, the dimethyl disulfide is coming primarily from the bacterial metabolism and not from the phytoplankton directly. The smell that these molecules are producing is strong, and it is unpleasant. At the high concentrations, the dimethyl sulfide is reeking of the rotting vegetables or the decaying seaweed. Some are describing it as being garlicky or sulfurous. If you could be somehow visiting this ocean world and be breathing the atmosphere, and you were to be assuming that the hydrogen was not killing you first, then the stench would be overwhelming. Imagine being standing downwind of a massive algae bloom that was covering the millions of the square miles, and all of it was releasing the dimethyl sulfide at once. That is what the air of this planet might be smelling like. But the smell is the least of the interesting aspects. The real question is what this molecule is telling us about the possibility of the life. On the Earth, we have been searching for the decades for any non-biological way to be making the dimethyl sulfide at the meaningful concentrations. We have been finding nothing. Every single one of the pathways is requiring the living cells. If the same is holding true on this distant world, then we are detecting the chemical signature of the life that has been being written in the starlight. How could the concentrations be being 10,000 times higher than those of the Earth? The atmosphere of the Earth is containing the dimethyl sulfide at less than 1 part per billion by the volume. If you are sampling the air from above the ocean, then you will be finding it, but barely. The molecule is breaking down very quickly. Its lifetime in our own atmosphere is averaging about 1 day. This has been being confirmed through the careful atmospheric chemistry studies. The sunlight is attacking it. The hydroxyl radicals are tearing it apart. The oxygen is converting it into the sulfur dioxide. The only reason that we are detecting it at all is because the phytoplankton are constantly replenishing the supply. This ocean world is showing the concentrations that are exceeding 10 parts per million. That is more than 10,000 times higher. To be putting this into the perspective, imagine if the carbon dioxide on the Earth were to be suddenly jumping from 400 parts per million to over 4 million parts per million. The entire planet would be becoming uninhabitable within the days. But the dimethyl sulfide is not the carbon dioxide. It is not driving the greenhouse warming in the same way. Its primary effect is chemical and not thermal. What could be explaining such high concentrations? One of the possibilities is involving the hydrogen atmosphere itself. On the Earth, the oxygen is dominating our atmosphere at 21%. The oxygen is highly reactive. It is destroying the dimethyl sulfide efficiently. This ocean world is having a hydrogen atmosphere with the minimal oxygen. The hydrogen is less reactive toward the dimethyl sulfide. The destruction pathways that are working on the Earth might not be working there. The molecule could be lasting for the weeks or the months instead of the days. The longer lifetime is meaning that less production is being needed to be maintaining the high concentrations. If the dimethyl sulfide is surviving for 10 times longer, then you are needing only 1/10 of the production rate to be achieving the same concentration. If it is surviving for 100 times longer, then you are needing 1/100th of the production rate. The scientists who are modeling this ocean world have been calculating that in a hydrogen atmosphere with the high carbon dioxide and the low oxygen, the dimethyl sulfide could be persisting for much longer than it is on the Earth. This is theoretical, but it is being based on the established atmospheric chemistry principles. But even when we are accounting for the longer lifetime, the numbers are still being staggering. 10 parts per million is requiring the enormous production. One research team estimated that you would need a biogenic flux, the rate at which organisms produce gas, thousands of times greater than what Earth's oceans provide. That's how extreme the conditions would have to be. That is suggesting either far more of the life per unit of the volume, or the far more efficient dimethyl sulfide production pathways, or both. Here is where the connection with the carbon dioxide is mattering. The Webb telescope had been detecting about 1% of the carbon dioxide in the atmosphere of this planet. That is 25 times higher than the 400 parts per million of the Earth. The high levels of the carbon dioxide can be affecting how the organisms are metabolizing the sulfur compounds. Some of the bacteria on the Earth are using the carbon dioxide in their metabolic pathways. Perhaps on this ocean world, the abundance of the carbon dioxide is driving the different biochemical pathways that are producing more of the dimethyl sulfide per cell. There is another factor. The temperature is affecting the rates of the chemical reactions. The warmer water is meaning the faster metabolism. If the oceans there are being warmer than those of the Earth, then the organisms might be growing faster, and they might be reproducing faster, and they might be producing the waste products faster. The average temperature of the oceans of the Earth is about 3.5 degrees Celsius. The models are suggesting that the surface of this ocean world could be ranging from 10 degrees to over 50 degrees Celsius, and it would be depending on the cloud cover and the strength of the greenhouse effect. At 30 degrees, the biological processes are running several times faster than they are at 3 degrees. If you combine all these factors, a hydrogen atmosphere that slows the destruction of dimethyl sulfide, high levels of carbon dioxide driving, altered metabolic pathways, warm oceans accelerating biological processes, and a potentially higher biomass density than Earth's oceans, then the outcome changes drastically. The multiplication of all these effects could explain why the concentrations are so much higher. Each of the factors alone might be providing a 2 times or a 5 times boost, but together they are multiplying and they are not adding. 2 times 5 times 3 times 4 is being equal to 120 times. If you are adding a few more of the factors, then you are reaching 10,000 times. But the critics are asking a different question. What if the high concentrations are proving that the signal is not a biological one? What if there is an abiotic, non-living chemical pathway that is producing the dimethyl sulfide efficiently in the hydrogen atmospheres? The laboratory experiments have been exploring this. The scientists had been mixing the methane and the hydrogen sulfide and had been exposing them to the ultraviolet light. They had been creating the trace amounts of the dimethyl sulfide, but the trace amounts are meaning the parts per billion and not the parts per million. The experiments are falling short by the factors of the thousands. Every single molecule is having a lifetime. It is the average time that it is existing before it is breaking apart. For the dimethyl sulfide in the atmosphere of the Earth, that lifetime is brutally short. One of the studies had been measuring it at 24 hours. Another had been finding 48 hours. The variation is depending on the local conditions like the intensity of the sunlight, the temperature, and the abundance of the oxidizing chemicals. But the conclusion is remaining the same. The dimethyl sulfide is not lasting for long. This is the confirmed science, and it has been being replicated in the numerous studies. There are 3 main processes that are destroying the dimethyl sulfide on the Earth. First, the hydroxyl radicals are attacking it. These radicals are the molecular fragments with the unpaired electrons, which is making them incredibly reactive. They are forming when the ultraviolet light is breaking apart the water molecules in the upper atmosphere. Once they have been being formed, the hydroxyl radicals are attacking almost any organic molecule that they are encountering. They are grabbing the hydrogen atoms and they are breaking the chemical bonds. The dimethyl sulfide is having 6 of the hydrogen atoms that are ripe for the taking. Second, the oxygen is directly reacting with the dimethyl sulfide. The reaction is slower than it is with the hydroxyl radicals, but it is still significant. The oxygen is combining with the sulfur atom, and it is creating the sulfur dioxide as the first step. Eventually, this pathway is leading to the formation of the sulfuric acid. That is why the burning of the sulfur-containing fossil fuels is creating the acid rain. The sulfur is becoming the sulfur dioxide, and then it is becoming the sulfuric acid, and it is then falling as the precipitation. The same chemistry is happening to the dimethyl sulfide naturally in the atmosphere. Third, the sunlight itself can be breaking the dimethyl sulfide apart. The photodissociation is occurring when a photon is carrying enough of the energy to be snapping the chemical bond. For the dimethyl sulfide, the ultraviolet wavelengths that are between 200 and 300 nanometers are doing the damage. These wavelengths are carrying enough of the punch to be breaking the carbon-sulfur bonds that are holding the molecule together. The pieces are flying apart and they are recombining with the other atmospheric chemicals. Now let's consider a hydrogen atmosphere. The hydroxyl radicals are still being forming, but they are doing so less efficiently. The hydrogen atmospheres are containing less of the water vapor to be breaking apart. Less of the water vapor is meaning fewer of the hydroxyl radicals, and fewer of the radicals is meaning the slower destruction of the dimethyl sulfide. The models are suggesting that the concentration of the hydroxyl radicals in the atmosphere of this ocean world might be being 1/10 or 1/100th of the levels of the Earth. The oxygen is presenting even more of the dramatic differences. This ocean world is having the minimal oxygen. The spectroscopic observations are showing no detectable features of the oxygen. That is meaning that the direct oxidation pathway that is destroying the dimethyl sulfide on the Earth is not working there. Eliminating one of the major destruction routes is automatically extending the lifetime of the molecule. The photodissociation is still happening. The star of the planet is putting out the ultraviolet light, though the red dwarfs are emitting less of the UV than our own sun is. The hydrogen atmosphere itself might be absorbing some of the UV before it is reaching the lower altitudes where the dimethyl sulfide is concentrating. The methane and the carbon dioxide are also absorbing the certain UV wavelengths, and they are providing the additional shielding. The net effect is that the dimethyl sulfide is experiencing less of the photochemical stress. If you are putting all of this together, then the dimethyl sulfide might be surviving for 10 times longer, and it could possibly be 100 times longer than it is on the Earth. Instead of 1 or 2 days, it might be lasting for the weeks or the months. That is transforming the production requirements. If you are only needing to be replenishing the molecule every few weeks instead of every single day, then you are needing much less of the biological activity to be maintaining the same atmospheric concentration. A factor of 10 in the lifetime is reducing the production requirements by a factor of 10. But here is the catch. Even with a 100 times longer lifetime, you are still needing the significant production to be maintaining 10 parts per million. The math is unavoidable. Something on this world is generating the dimethyl sulfide at the rates that are dwarfing anything that we are seeing on the Earth. The extended lifetime is helping to be explaining how the concentration is staying so high, but it is not eliminating the need for a powerful source. The scientists are trying to be pinning down the exact lifetime numbers through the detailed atmospheric modeling. They are inputting the observed concentrations of the methane, the carbon dioxide, and the hydrogen. They are calculating the photochemistry reaction by reaction, and they are tracking how each of the molecules is interacting with the others. They are estimating the flux of the UV from the star. They are modeling the temperature and the pressure at the different altitudes. The result is a prediction of the lifetime of the dimethyl sulfide under those specific conditions. The early models are suggesting the lifetimes that are between 10 and 100 days, but the uncertainty is remaining large. Not everyone is believing that the signal of the dimethyl sulfide is meaning the life. A growing number of the scientists are pointing to an alternative explanation. What if this world is having no oceans at all? What if the surface is the molten rock that is being wrapped in a hydrogen atmosphere? The magma oceans could be producing some of the same chemical signatures as the living oceans. This alternative explanation is coming from the detailed climate modeling that had been being published in the early 2024. Here is how the magma oceans might be working. The planet is receiving the substantial starlight despite being orbiting a dim red dwarf. A thick hydrogen atmosphere is creating a powerful greenhouse effect. Even though the hydrogen is not as efficient as the carbon dioxide at trapping the heat, enough of it is creating the serious warming. The models are suggesting that the surface temperatures could be exceeding 800 degrees Celsius under these conditions. This is theoretical, and it is being based on the energy balance calculations and the known atmospheric properties. At those temperatures, the rock is melting. The granite is melting at around 1,200 degrees. The basalt is melting at around 1,100 degrees. But the rocks are the complex mixtures. Some of the minerals are melting at the lower temperatures. A planetary surface at 800 degrees would not be being fully molten, but it could be having the widespread lava flows, the lava lakes, and the molten regions that are covering the large fractions of the surface. Picture Io, which is the volcanic moon of Jupiter, but it is being scaled up to 2.5 times the size of the Earth. The magma is interacting with the atmospheres in the complex ways. The volcanic gases are bubbling up through the molten rock. These gases are including the water vapor, the carbon dioxide, the sulfur dioxide, and the hydrogen sulfide. When the hydrogen sulfide is entering a hydrogen-rich atmosphere, the chemistry is happening. At the high temperatures, the hydrogen sulfide can be reacting with the carbon-containing molecules to be forming the organic sulfur compounds. The laboratory experiments have been demonstrating this. The yields are low, but the continuous volcanic outgassing could be maintaining the steady production. One of the research teams had been running the numbers. They had been modeling a planet with a magma surface, a hydrogen atmosphere, and the volcanic outgassing rates that were being similar to the most active of the volcanic periods of the Earth. Their model had been producing the dimethyl sulfide through the abiotic chemistry, but the concentrations had been falling short by the factors of 10 to 100 compared to the observations. They could be making the dimethyl sulfide without the life, but not enough of it. The gap is suggesting that the biology might still be being needed, but it is not ruling out the enhanced volcanic processes that we are not fully understanding. There is another clue: the ammonia. On the Earth, the nitrogen-rich atmospheres are producing the ammonia when the lightning or the other energy sources are combining the nitrogen with the hydrogen. The ammonia is also being produced by the life. Many of the bacteria are generating the ammonia as a waste product. The models are predicting that a habitable ocean world should be having the detectable ammonia, yet the observations are showing none. The absence of the ammonia has been being confirmed through the spectroscopic analysis. The models of the magma oceans are explaining the missing ammonia naturally. The nitrogen is dissolving into the molten rock under the high pressure. The technical term is the nitrogen partitioning into the melt phase. If the surface is being molten, then the atmospheric nitrogen is getting absorbed into the magma. This is depleting the ammonia from the atmosphere. You are ending up with a planet that is having the nitrogen that is being locked in the surface rather than being floating in the air. This is matching the observations perfectly. The models of the ocean worlds are struggling with the missing ammonia. If the liquid water is existing at the surface, then the nitrogen should be staying in the atmosphere. The ammonia should be being forming through the chemical reactions and the biological processes. Its absence is becoming a puzzle. Some of the scientists are arguing that the certain metabolic pathways could be consuming the ammonia as fast as it is being forming. But this is requiring the special conditions. The explanation of the magma ocean is simpler. It is requiring no special biology, and it is just being the basic chemistry. But the models of the magma oceans are facing their own challenges. They are struggling to be explaining the methane that has been being detected in the atmosphere. The methane should not be being stable at the high temperatures. It is breaking down into the carbon and the hydrogen above about 700 degrees Celsius. To be maintaining 1% of the methane in the atmosphere is requiring either the continuous production or the cooler temperatures than the models of the magma oceans are predicting. Either of the options is creating the problems for the hypothesis of the magma ocean. The debate is continuing. Some of the scientists are favoring the explanation of the magma ocean because it is explaining the missing ammonia. Others are favoring the explanation of the ocean world because it is explaining the abundant methane and the dimethyl sulfide. Both of the camps are agreeing that more of the observations are being needed. The next round of the observations from the Webb telescope might be detecting the other molecules that are settling the question. The certain chemicals would only be being existing in the magma conditions. The others would only be being existing with the liquid water. What if the planet is having the water, but the atmosphere is being more alien than anyone had been expecting? The hydrogen is dominating the atmosphere of this planet. The spectroscopic observations are confirming this. The absorption features and the way that the starlight is getting filtered are all pointing to the massive amounts of the hydrogen and the helium. This is creating a fundamental problem for the life as we are knowing it. The atmosphere of the Earth is being 78% of the nitrogen, and it is being 21% of the oxygen, and it is being just the trace amounts of the other gases. There is no hydrogen at all at the ground level. The hydrogen is too light. It is escaping the gravity of the Earth and is drifting into the space. But this ocean world is more massive. Its stronger gravity is holding on to the hydrogen. The life on the Earth had been evolving in a nitrogen-oxygen environment. Our proteins, our enzymes, and our cellular machinery are all assuming the certain atmospheric chemistry. The oxygen is serving as the final electron acceptor in the respiration, which is the process that is powering most of the complex life. Without the oxygen, you are being limited to the anaerobic metabolism. That is working fine for the bacteria and some of the simple organisms, but the complex multicellular life, which is the kind that is building the civilizations, is needing the oxygen or something that is equivalent. A hydrogen atmosphere is changing everything. The hydrogen is not just being inert like the nitrogen. It is actively participating in the chemistry. It is reducing the other molecules, which is the opposite of the oxidation. This is affecting what of the chemical reactions are being possible. Some of the reactions that are proceeding easily in the oxygen-rich atmospheres are becoming difficult or impossible in the hydrogen-rich ones. The other of the reactions that are never happening on the Earth are becoming favorable. But here is the surprising part. The life might not only be tolerating the hydrogen atmospheres, but it might be thriving in them. The recent laboratory experiments had been testing whether the microbes of the Earth could be surviving in the pure hydrogen. The results had been shocking the researchers. The bacteria and the yeast that are normally never encountering the hydrogen had been growing just fine when they had been being exposed to the 100% hydrogen atmospheres. This is the confirmed experimental data, and it has been being published in the peer-reviewed journals. The organisms had not been growing faster, but they had not been dying either. They had been adapting. The hydrogen is offering the metabolic opportunities. Some of the bacteria on the Earth are using the hydrogen as an energy source. They are combining the hydrogen with the carbon dioxide to be making the methane, and they are gaining the energy in the process. These methanogens are living in the deep-sea vents, in the swamps, and in the guts of the animals. They are proving that the hydrogen-based metabolism is working. On a planet with the abundant atmospheric hydrogen, these metabolic pathways might be dominating. The question is becoming whether the complex organisms can be evolving in such environments. On the Earth, the jump from the single-celled to the multicellular life had been coinciding with the rising levels of the oxygen. The Great Oxidation Event, which was 2.4 billion years ago, had been filling our atmosphere with the oxygen from the photosynthetic bacteria. Within a few hundred of the million years, the complex life had been emerging. The correlation is not proving the causation, but the timing is suggestive. Some of the scientists are arguing that the high energy density of the oxygen is making it ideal for powering the complex life. Others are arguing that any of the sufficiently energetic metabolism could be working. The hydrogen metabolism is providing less of the energy per reaction than the oxygen metabolism is, but it is still providing the energy. Maybe the complex life is evolving more slowly in the hydrogen atmospheres. Maybe it is taking the different forms. Maybe it is never getting beyond the microbial colonies. We are not knowing because we are having only one single example of the life to be studying. The hydrogen atmosphere on this ocean world had likely been coming from the formation of the planet. When the planets are forming, then they are accreting the gas from the surrounding nebula. The large planets are capturing more of the gas. If a planet is growing massive enough quickly enough, then it is capturing the huge amounts of the hydrogen and the helium before the radiation of the star is blowing away the nebula. This ocean world had probably been capturing several of the Earth masses of the hydrogen during its formation. This is theoretical, but it is being well supported by the models of the planet formation. Over the time, the atmospheric escape is slowly stripping away the hydrogen. The high-energy particles from the star are knocking the hydrogen atoms out of the upper atmosphere. They are gaining enough of the speed to be overcoming the gravity of the planet, and they are drifting away. The red dwarf stars are producing the frequent flares that are accelerating this process, yet this world had been retaining its hydrogen atmosphere over the billions of the years. That is suggesting either that the planet is young or that the atmosphere is thick enough to be weathering the losses. The thickness is mattering for the habitability. A thin hydrogen atmosphere would not be trapping much of the heat. A thick one is creating the extreme greenhouse warming. The challenge is finding the right balance. If it is too thin, then any liquid water is freezing. If it is too thick, then the surface pressures are becoming crushing. The models are suggesting that this planet is sitting near the very edge of the habitability. The small changes in the atmospheric mass could be tipping it from being habitable to being uninhabitable. Why are some of the scientists thinking that this world is resembling Neptune more than it is the Earth? Neptune is having a radius that is about 4 times larger than that of the Earth. Its mass is 17 times that of our own. Its atmosphere is mostly being the hydrogen and the helium, with about 2% of the methane. Deep below the atmosphere is lying a mantle of the water, the ammonia and the methane ices. And deeper still is being a rocky core that is perhaps being slightly larger than the Earth. Neptune is not a gas giant like Jupiter. It is an ice giant that is being dominated by the volatile compounds rather than the hydrogen gas. This ocean world is sharing many of the characteristics with Neptune despite being smaller. The density is telling a part of the story. The density of Neptune is sitting at 1.6 grams per cubic centimeter. This ocean world is measuring at 2.67 grams per cubic centimeter. The Earth is at 5.5 grams per cubic centimeter. The progression is clear. This planet is falling between Neptune and the Earth in its density. The simple calculations are showing that it must be containing less of the rock than the Earth is, and more of the rock than Neptune is. But what is filling the gap? The interior structure models are providing the answers. The scientists are inputting the observed mass and the radius. They are adding the constraints from the planetary science. The rocky materials are having the certain densities. The water ice under the pressure is having a different density. The hydrogen gas that has been being compressed to the high pressure is having yet another density. By testing the different combinations, the scientists are narrowing down the plausible interior structures. This is theoretical, but it is being grounded in the physics and the chemistry that have been being established through the laboratory experiments and the quantum mechanics. Most of the models are converging on a similar picture. There is a rocky core that is being 1 to 3 times the mass of the Earth. Above that is being a thick mantle of the high-pressure ice and possibly the liquid water. This layer might be being 1,000 to 2,000 miles thick, and above that is being a hydrogen-helium atmosphere that is being thousands of the miles deep, and it is gradually thinning as the altitude is increasing. This structure is looking nothing like the Earth. It is looking like a small Neptune with slightly more of the rock and less of the gas. If this picture is being correct, then the planet is having no solid surface in any meaningful sense. If you were to be descending through the atmosphere, then you would be finding the increasing pressure and the temperature. Eventually, the hydrogen is becoming so dense that it is behaving like the liquid, and deeper still, the ice mantle is beginning. But there is no sharp boundary, and there is no place where you could be landing a spaceship. The transition from the atmosphere to the ice is happening gradually over the hundreds of the miles. This is how Neptune is working. The observations are suggesting that this ocean world is working similarly, but this interpretation is conflicting with the detection of the dimethyl sulfide. Neptune is not producing the dimethyl sulfide. Its atmosphere is containing the methane, the ethane, the acetylene, and the other hydrocarbons. No sulfur-based organic molecules have ever been being detected there. If this distant world is resembling Neptune, then why is it showing the chemistry that Neptune is lacking? One of the possibilities is a liquid water layer that is being sandwiched between the ice mantle and the hydrogen atmosphere. At the certain depths, the pressure and the temperature could be allowing the liquid water to be existing. This water would not be being in contact with the space or the air like the oceans of the Earth are. It would be being trapped beneath the thousands of the miles of the hydrogen, but it could still be hosting the life. The microbes that were floating in this buried ocean could be producing the dimethyl sulfide. The gas would be bubbling up through the atmosphere, and it would be reaching the altitudes where the telescopes are detecting it. The critics are pointing out the problems with this scenario. How would the life be starting in a buried ocean? On the Earth, the life had likely been beginning in the shallow pools or near the hydrothermal vents, which are the places where the energy and the chemicals are concentrating. A buried ocean is lacking these features. The energy would be being scarce. The nutrients would be being limited. Starting the life in such conditions is seeming to be implausible. But once it had been being started, and it had perhaps been doing so through some unknown mechanism, the life might be spreading and be thriving. Another of the issues is the methane. Neptune is having 2% of the methane. This ocean world is having 1%. On Neptune, the methane is coming from the interior of the planet, and it is being released through the convection and the atmospheric mixing. If this world is resembling Neptune, then its methane might be having the same source. But the models of the ocean worlds are explaining the methane differently. They are proposing the biological production with the methanogens that are creating the methane from the hydrogen and the carbon dioxide. Both of the explanations are fitting the observations, and it is making it hard to be distinguishing between them. The debate is boiling down to whether this planet is having a surface and the oceans, or if it is lacking both. The spectroscopy is telling us what of the chemicals are existing in the atmosphere. It is not directly being revealing what is lying beneath. We are inferring the surface conditions from the atmospheric composition, but the inferences can be being wrong. The multiple explanations can be fitting the same data. Breaking this degeneracy is requiring the additional observations that are probing deeper into the nature of the planet. What is happening when the scientists are examining the mysterious absence of a crucial atmospheric component? The concept of the Hycean worlds had been emerging in 2021 from the theoretical work that had been led by the researchers at Cambridge. They had been asking a simple question: can the planets that are larger than the Earth but are smaller than Neptune be hosting the liquid water oceans despite having the hydrogen atmospheres? The conventional wisdom had been saying no. The hydrogen atmospheres had been being thought to be creating the runaway greenhouse effects that were making the surfaces too hot, but the detailed modeling had been revealing a different possibility. This is the theoretical work, and it is being based on the established climate physics. The key is the formation of the clouds. High in the atmosphere, the water vapor can be condensing into the clouds. These clouds are reflecting the starlight back into the space before it is heating the surface. If enough of the clouds are forming, then they could be keeping the planet cool despite a strong greenhouse effect that was lower in the atmosphere. The sweet spot is existing when the cloud cover is reaching about 50 to 70% of the planet. If there is too little of the cloud, then the surface is overheating. If there is too much of the cloud, then the starlight cannot be penetrating to be supporting the photosynthesis or be heating the water. The Hycean worlds would be having the surface pressures that were being between 100 and 1,000 times the atmospheric pressure of the Earth. That is sounding crushing, but the oceans of the Earth are already experiencing such pressures just a few miles down. The life is thriving in the deep ocean despite the pressures that are being over 1,000 times the surface levels. If the life can be handling those pressures in the oceans of the Earth, then perhaps it could be handling them at a Hycean surface, where the pressure is coming from the atmosphere instead of the depth of the water. The temperature is the trickier of the constraints. The water is staying liquid between 0 and 100 degrees Celsius at the surface pressure of the Earth. But at the higher pressures, the water is staying liquid at the higher temperatures. At 100 atmospheres of the pressure, the water is boiling at 311 degrees Celsius instead of 100. At 200 atmospheres, the boiling point is rising to 365 degrees. This has been being confirmed through the laboratory pressure-temperature phase diagrams for the water. The upper limit is coming at the critical point of the water. Above 374 degrees Celsius and 221 atmospheres, the water is entering a supercritical state where the liquid and the gas phases are merging. The supercritical water is having the bizarre properties. It is flowing like a gas, but it is dissolving the substances like a liquid. It could potentially be supporting the life, but the life as we are knowing it is relying on the distinct properties of the liquid water. Going supercritical might be making the habitability impossible. The Hycean models are suggesting that the surface temperatures that are between 10 and 70 degrees Celsius are being possible under the right conditions. That range is being compatible with the life. The hottest of the environments of the Earth, like the deep-sea hydrothermal vents, are reaching over 100 degrees Celsius, and they are hosting the thriving bacterial communities. If the Hycean oceans are staying cooler than that, then the life is seeming to be plausible. But establishing those temperatures is requiring the precise balancing of the greenhouse warming and the cloud cooling. The hydrogen atmosphere is serving the multiple roles. It is providing the greenhouse warming to be preventing the freezing. It is protecting from the harmful space radiation. It is offering the metabolic fuel for the hydrogen-using organisms. But it is also blocking the ultraviolet light that is driving the photosynthesis on the Earth. The Hycean life might be needing to be adapting to the dimmer, redder light that is penetrating the atmosphere. The red dwarf stars are emitting mostly the red and the infrared light anyway, so this might not be being a problem. The availability of the nutrients is posing another challenge. On the Earth, the continental weathering is releasing the minerals into the rivers that are flowing to the oceans. These minerals are providing the nutrients for the marine life. The Hycean worlds might be lacking the continents entirely, and they might be being without the weathering. How are the nutrients reaching the ocean? Perhaps the volcanic activity on the seafloor is releasing the minerals directly into the water. Perhaps the ocean is being supplied from below, with the chemicals that are seeping up from the rocky mantle that is beneath. One of the intriguing of the predictions is that the Hycean worlds should be showing the specific atmospheric signatures. There should be high levels of methane from biological production and high levels of carbon dioxide from volcanic outgassing or biological respiration. There should also be detectable water vapor and potentially biosignature gases like dimethyl sulfide or methyl chloride. This ocean world is matching the predicted pattern almost perfectly. The alignment that is between the prediction and the observation is what is exciting the researchers. How might the thick atmospheres be creating the stable conditions. The greenhouse effects are getting a bad reputation. The discussions of the climate change are focusing on the runaway greenhouse warming as being catastrophic. But the greenhouse effects are not being inherently bad. They are what are making the Earth habitable in the first place. Without our natural greenhouse effect, the average temperature of the Earth would be being -8 degrees Celsius. The oceans would be freezing solid. Instead, the greenhouse gases are keeping us at a comfortable +15 degrees Celsius. This is the basic atmospheric physics, and it has been being confirmed through the decades of the measurements. The mechanism is straightforward. The sunlight is passing through the atmosphere and is warming the surface. The warm surface is radiating the energy back as the infrared light. The greenhouse gases are absorbing this infrared, and they are trapping the heat in the lower atmosphere. The gases are eventually re-radiating the energy, but some of it is going back down toward the surface. This is creating a warming effect. More of the greenhouse gas is meaning more of the warming. The relationship is not being linear, but it is being predictable. On the Earth, the carbon dioxide and the water vapor are providing most of the greenhouse effect. The methane and the nitrous oxide are contributing the smaller amounts. These gases are working because their molecular structures are absorbing the infrared wavelengths. Not all of the gases are doing this. The nitrogen and the oxygen, which are making up most of our atmosphere, are being transparent to the infrared. They are not being contributing to the greenhouse warming. The hydrogen and the helium are similarly being transparent. You are needing the other molecules that are being mixed in. The hydrogen atmosphere of this ocean world is not trapping much of the heat directly, but it is containing about 1% of the methane and 1% of the carbon dioxide. That might not be sounding like much, but it is enough. The atmosphere of the Earth is containing only 400 parts per million of the carbon dioxide, which is 0.04%. This distant planet is having 25 times more of the carbon dioxide than the Earth is. The methane is an even more powerful greenhouse gas than the carbon dioxide is. Molecule for molecule, 1% of the methane is providing the serious warming. Here is where the hydrogen is becoming important. The sheer mass of the hydrogen atmosphere is increasing the pressure at the surface. The higher pressure is meaning the denser air. The denser air is holding more of the heat. It is also slowing the escape of the infrared radiation. The photons that are trying to be leaving the planet are getting absorbed and are being re-emitted multiple times before they are finally making it to the space. Each of the absorption-emission cycles is delaying the loss of the heat. The result is that even though the hydrogen itself is not trapping the infrared well, a thick hydrogen atmosphere is still creating the significant greenhouse warming through the effects of the pressure alone. Models show that a hydrogen atmosphere containing 1% carbon dioxide and 1% methane can maintain surface temperatures warm enough for liquid water. That's possible even on a planet receiving less starlight than Earth. This is extending the habitable zone outward from the star. The planets that would be being too cold with the Earth-like atmospheres are becoming warm enough with the hydrogen atmospheres. This is flipping the conventional thinking about where to be looking for the life. But there is a catch. The greenhouse effect must be being strong, but not too strong. Venus is demonstrating what is happening when the greenhouse warming is going out of control. Venus is receiving twice of the sunlight that the Earth is, and it is having a crushing carbon dioxide atmosphere. The surface temperatures are reaching 470 degrees Celsius, and it is being hot enough to be melting the lead. The greenhouse effect had been running away. All of the water had been evaporating, and it had been creating more of the greenhouse gas, and it had been creating more of the warming, and it had been creating more of the evaporation. It was a positive feedback loop with no braking mechanism. This ocean world is sitting right on the edge. The computer models are showing that the small changes in the atmospheric composition or the cloud cover could be pushing it into the runaway greenhouse territory. If the clouds are failing to be forming, then the surface temperatures are spiking. The water is evaporating and it is creating more of the greenhouse warming. Once it has been being started, the process might be being irreversible. Alternatively, if the clouds are becoming too thick, then they are blocking too much of the starlight. The surface temperatures are dropping and the water is freezing, and the frozen surfaces are reflecting more of the light, and it is creating more of the cooling. This is another of the runaway processes, but it is in the opposite direction. The fact that this planet is apparently maintaining the stable conditions is suggesting a balancing mechanism. Perhaps the biological processes are helping to be stabilizing the climate. On the Earth, the phytoplankton are producing the dimethyl sulfide, which is seeding the clouds. More of the warming is meaning more of the phytoplankton. More of the phytoplankton is meaning more of the dimethyl sulfide. More of the dimethyl sulfide is meaning more of the clouds. And more of the clouds is meaning more of the cooling. This negative feedback might be preventing the runaway warming. The same mechanism could be working on this ocean world. If so, then the life would not just be existing there. The life would be actively regulating the climate of the planet, and it would be making it habitable. Why is the absence of the ammonia splitting the scientific opinion? The ammonia should be being there. The multiple models are predicting it, yet the observations are showing no trace. This absence has been becoming one of the most debated of the aspects of the atmosphere of this planet. The ammonia is the nitrogen and the hydrogen that have been being combined. The formula is being written as one nitrogen atom that is being bonded to 3 of the hydrogen atoms. In a hydrogen-rich atmosphere that is receiving the energy from the starlight or the lightning, the formation of the ammonia is being expected. This is the confirmed chemistry, and it has been being observed in the laboratory experiments and in the atmospheres of the gas giants in our own solar system. Jupiter is having the ammonia, so is Saturn and Uranus and Neptune. Wherever you are finding the hydrogen and the nitrogen together with enough of the energy to be driving the reactions, the ammonia is appearing. The spectroscopic observations of these planets are showing the strong absorption features of the ammonia. No one is questioning whether the ammonia is there. The question is why it is being missing from this ocean world when it should be being present. One of the explanations is invoking the biological consumption. Some of the bacteria on the Earth are metabolizing the ammonia as an energy source. The nitrifying bacteria are converting the ammonia to the nitrite and then to the nitrate. They are gaining the energy from these reactions. In an ocean that was full of such bacteria, the ammonia could be being removed from the atmosphere as fast as it is being forming. The ocean is acting as a sink. The atmospheric ammonia is dissolving into the water. The bacteria are consuming it. More of the atmospheric ammonia is dissolving to be replacing what had been being consumed. An equilibrium is being establishing where the concentrations of the ammonia are staying near zero. This explanation is fitting the hypothesis of the ocean world nicely. It is requiring the life, but the life is what the signal of the dimethyl sulfide is suggesting anyway. The two pieces of the evidence are supporting each other. The biological metabolism is explaining both the presence of the dimethyl sulfide and the absence of the ammonia. It is creating a self-consistent picture, but it is requiring us to be assuming that the life is existing, which is what the scientists are trying to be proving. The circular reasoning is becoming a risk. The alternative explanation is invoking the chemistry without the biology. If the surface is being the molten rock, then the nitrogen is dissolving into the magma. The experimental studies of the volcanic systems are showing that at the high temperatures and the pressures, the nitrogen is partitioning into the melt phases rather than staying in the gas phase. A magma ocean would be sucking the nitrogen out of the atmosphere. Without the atmospheric nitrogen, the ammonia cannot be forming. The absence of the ammonia is becoming the evidence for a magma ocean rather than a water ocean. This explanation is fitting the hypothesis of the magma ocean nicely. It is requiring no life. It is explaining the missing ammonia through the straightforward chemistry. But it is struggling to be explaining the dimethyl sulfide. As it has been being discussed earlier, the models of the magma oceans can be producing the small amounts of the dimethyl sulfide through the abiotic chemistry. Whether they can be producing enough is remaining questionable. The hypothesis of the magma ocean is explaining one of the mysteries while it is struggling with another. There is a third of the possibilities that is being rarely discussed. Maybe the spectroscopic observations had simply been missing the ammonia. The ammonia is having the absorption features at the specific wavelengths. If those wavelengths had not been being observed, or if the noise had been obscuring the signal, then the ammonia could be being present but be being undetected. However, the James Webb Space Telescope had been observing the multiple wavelength ranges. The instruments are having the sufficient sensitivity to be detecting the ammonia at the expected concentrations. The multiple research teams had been analyzing the data independently. All of them had been reaching the same conclusion. There is no ammonia. The missing ammonia is forcing the scientists to be choosing between the competing scenarios. Either the life is consuming it, or the magma is absorbing it, or some third unknown process is removing it. Each of the choices is leading down a different path for understanding this world. There is the ocean world with the life, and there is the magma ocean without the life, or there is something that is entirely unexpected. The scientific community is remaining split. Some of the researchers are strongly favoring the biological explanation. Others are leaning toward the magma oceans. A third of the groups is arguing that the data is remaining too ambiguous to be choosing. What they are all agreeing on is that more of the observations are being desperately needed to be breaking the deadlock. Imagine an ocean where every single drop of the water is containing 1,000 times more of the microbes than the most productive of the seas of the earth. That is what the numbers are demanding. The concentrations of the dimethyl sulfide that have been being observed are requiring the staggering amounts of the biological activity. On the Earth, the phytoplankton are floating in the sunlit surface waters, which is about the top 600 feet where the light is penetrating. Below that, the darkness is reigning, the photosynthesis is stopping. On this ocean world, the same depth limit would be applying unless something is changing the rules. One of the possibilities is simply the density. The oceans of the Earth are containing roughly 1 million of the bacterial cells per milliliter of the seawater. That is sounding like a lot until you are considering that the fertile soil is containing 1 billion of the cells per gram. The ocean water is relatively sparse in the microbial life compared to the other environments. Perhaps this distant ocean is more like the fertile soil. There could be the dense bacterial mats that are floating in the water column. There could be the thick biofilms that are coating every available surface. There could be a microbial density that is 1,000 times higher than that of the oceans of the Earth. This is the speculation, but the math is requiring it. Another of the possibilities is involving the different organisms entirely. On the Earth, the dimethyl sulfide is coming primarily from the eukaryotic phytoplankton, which are the organisms with the complex cells that are containing the nuclei and the organelles. These had been evolving relatively late in the history of the Earth, which was about 2 billion years ago. Before that, the simpler bacteria had been dominating. Perhaps this ocean world is hosting the bacteria that are producing the dimethyl sulfide through the different metabolic pathways. The bacteria can be evolving quickly, and they can be adapting to the local conditions within the thousands of the generations. An ocean that was full of the dimethyl sulfide producing bacteria could be generating the observed concentrations. The hydrogen atmosphere is opening the unique metabolic possibilities. Some of the bacteria of the Earth that are called the methanogens are combining the hydrogen gas with the carbon dioxide to be producing the methane. They are gaining the energy from this reaction. It is working well in the environments without the oxygen. Perhaps the similar organisms on this ocean world are combining the hydrogen with the sulfur compounds to be producing the dimethyl sulfide directly. This would be being more efficient than the pathway of the Earth, where the dimethyl sulfide is forming as a byproduct rather than as a primary metabolic product. The temperature is mattering too. The warmer water is meaning the faster metabolism. The chemical reactions are roughly doubling in their speed for every 10 degrees Celsius of the increase in the temperature. If the surface of this ocean is averaging 30 degrees Celsius compared to the 4 degrees of the Earth, then the reactions are proceeding about 8 times faster. 8 times the faster metabolism is meaning 8 times more of the production of the dimethyl sulfide per cell. If you are multiplying that by the higher cell density, then you are starting to be reaching the required production rates. There is also the question of the evolutionary pressure. On the Earth, the phytoplankton are producing the dimethyl sulfonionpropionate to be regulating the salt balance. The dimethyl sulfide is accidental, but what if the organisms on this world are using the dimethyl sulfide for the communication? The bacteria on the Earth are using the chemical signals to be coordinating their behavior, which is a process that is called the quorum sensing. When enough of the bacteria are gathering in one place, then their chemical signals are reaching the threshold concentrations that are triggering the collective responses. Perhaps the dimethyl sulfide is serving this function there with the organisms that are deliberately producing it in the large quantities. The availability of the energy is driving the biological productivity on the Earth. The photosynthesis is capturing the sunlight and is converting it to the chemical energy that is powering the food chain. This ocean world is receiving the similar amounts of the starlight as the Earth is. The red dwarf star is emitting more of the red and the infrared light compared to the broader spectrum of our own Sunday. But some of the organisms of the Earth are photosynthesizing by using the red light efficiently. The purple bacteria and some of the cyanobacteria are thriving in the red-dominated environments. The life there might have been adapting similarly. The availability of the nutrients is equally important on the Earth. The upwelling is bringing the nutrients from the deep water to the surface, and it is fueling the productive regions like the coast of California and the waters that are around Antarctica. Without the continents to be creating the coastal upwelling, this ocean world might be relying on the different mechanisms. Perhaps the volcanic activity on the sea floor is releasing the nutrients directly into the water column. Perhaps the ocean is being supplied from below with the chemicals that are seeping up from the rocky mantle that is beneath. Either way, the high productivity is requiring the high supply of the nutrients. But could the life even be surviving the temperature swings that this planet is experiencing? The life on the Earth is surviving the astonishing extremes. The bacteria are thriving in the boiling hot springs at Yellowstone where the water is reaching 90 degrees Celsius. The other of the organisms are surviving in the Antarctic ice at -40 degrees. The tardigrades, which are the microscopic animals that are called the water bears, can be enduring the temperatures from near the absolute zero to 150 degrees Celsius. The life is tougher than most of the people are realizing. These extremes have been being confirmed through the direct observation and the laboratory testing. But this ocean world might be pushing even beyond the extremes of the Earth. The climate models are showing that depending on the atmospheric conditions, the surface temperatures could be ranging from 10 degrees Celsius to over 70 degrees Celsius. The elliptical orbit is causing the variations throughout each of the 33-day years. At the closest approach to the star, the temperatures are spiking. At the farthest distance, they are dropping. The difference might be exceeding 20 degrees Celsius between the orbital extremes. Any of the life there must be handling these swings, or it must be finding the ways to be avoiding them. The organisms of the Earth are using the several strategies for the tolerance of the temperature. Some of them are entering the dormancy during the unfavorable conditions. The bacterial spores can be surviving for the thousands of the years in the suspended animation, and they can be waiting for the conditions to be improving. When the temperatures are becoming favorable again, then they are reactivating and are resuming their growth. Perhaps the organisms on this ocean world are sporulating during the temperature extremes, and then they are blooming during the moderate periods. This would be creating the cycles of the biological activity that were being synchronized with the orbit. The other of the organisms are using the biochemical adaptations. The proteins are folding into the specific shapes to be performing their functions. The temperature is affecting the stability of the proteins. If it is too hot, then the proteins are unfolding and they are losing their function. If it is too cold, then the enzymes are slowing down, but the thermophilic organisms, which are the heat-loving bacteria, are producing the proteins with the extra chemical bonds that are stabilizing their structure at the high temperatures. The psychrophilic organisms, which are the cold-loving bacteria, are using the flexible proteins that are remaining active even when it is cold. The life on this ocean world might be combining both of the strategies, and it might be producing the proteins that are being stable across the wide ranges of the temperature. The ocean itself is providing the buffering. The water is having the high heat capacity, which is meaning that it is taking a lot of the energy to be changing its temperature. The large bodies of the water are warming slowly and are cooling slowly. Even if the air temperatures are swinging wildly, the ocean temperatures are remaining more stable. The oceans of the Earth are showing the daily temperature variations of just 1 or 2 degrees at the surface, despite the air temperature swings of 10 or 20 degrees. An ocean on this distant world would similarly be buffering the changes in the temperature, and it would be smoothing out the orbital variations. The depth is offering another refuge. On the Earth, the surface waters are fluctuating in their temperature with the seasons and the weather. The deeper waters are remaining stable year-round. Below about 600 feet, the temperature of the ocean is barely changing. It is staying at around 4 degrees Celsius in most of the places, regardless of what is happening at the surface. The life could be retreating to the stable deep water during the temperature extremes, and it could then be rising to the productive surface layer during the favorable periods. The vertical migration is common in the oceans of the Earth. Many of the organisms are descending during the day and are rising at the night, but the extreme temperatures are creating another problem. The rates of the chemical reactions are changing with the temperature. And it is not just the biological reactions, but all of the chemistry. At the higher temperatures, the dimethyl sulfide is breaking down faster. At the lower temperatures, it is persisting for longer. The varying lifetime throughout the orbital cycle is complicating the atmospheric modeling. The scientists must be accounting for the time-dependent chemistry, where the reaction rates are shifting as the planet is moving along its elliptical path. There is the evidence that the life is adapting to the cyclic extremes better than it is to the constant extremes. The organisms can be preparing for the predictable changes. Before the winter is arriving, the trees are moving the nutrients into their roots and are shedding their leaves. Before the dry season is coming, some of the fish are burying themselves in the mud and are entering the hibernation. The key is the predictability. If the 33-day cycle is repeating reliably, then the life could be evolving the responses that were being triggered by the environmental cues like the changing intensity of the light or the temperature. But the temperature is not the only challenge that this planet is presenting. What about the daylight problem? When a planet is orbiting very close to its star, the gravitational forces are reshaping everything. The star is pulling harder on the near side than it is on the far side. This difference in the pull, which is called the tidal force, is creating the friction inside of the planet. Over the millions of the years, this friction is slowing down the rotation of the planet. Eventually, the planet is rotating at exactly the same rate that it is orbiting. One of the sides is permanently facing the star. The other side is facing the eternal darkness. This is the confirmed physics, and it has been being observed throughout our own solar system. Our own moon is tidally locked to the Earth. The same side of it is always facing us. We are never seeing the far side from the Earth without the spacecraft. Mercury is nearly tidally locked to the Sun, and it is rotating 3 times for every 2 of its orbits. Most of the planets that are orbiting close to the red dwarfs are being expected to be fully tidally locked. The timescale is depending on the distance, the mass of the planet, and the internal structure. For this ocean world that is orbiting just 13 million miles from its star, the tidal locking had almost certainly been occurring within the first few hundred of the million years. This is theoretical, but it is being strongly supported by the calculations. The tidal locking is creating the dramatic consequences. The day side is receiving the constant starlight, and it is never experiencing the night. The temperatures there are remaining high continuously. The night side is receiving no direct starlight ever, and it is remaining frozen. Between these extremes is lying a twilight zone, which is a ring around the planet where the star is hanging at the horizon. This terminator region is experiencing neither the full day nor the full night. It might be being the only place with the moderate temperatures. On the Earth, the daylight cycles are driving the weather, the ocean currents, and the biological rhythms. The plants are photosynthesizing during the day and are respiring at the night. The animals are coordinating their activity to the circadian rhythms. A tidally locked world is lacking these cycles. The life there would be needing to be adapting to the constant conditions, whether they were being always light or always dark. The twilight zone might be hosting the most diverse of the life, and it might be benefiting from both the illumination and the moderate temperatures. But the atmospheric circulation is changing everything. A thick atmosphere is transporting the heat from the day side to the night side. On the Earth, the atmospheric circulation is creating the wind patterns, the jet streams, and the weather systems. On a tidally locked planet, the circulation would be being far more extreme. The air that was being heated on the day side would be rising and would be flowing toward the night side. The cold air on the night side would be sinking and would be flowing back toward the day side. The result is a planet-wide circulation cell with the winds that are potentially reaching the hundreds of the miles per hour. The computer models are showing that a thick hydrogen atmosphere could be transporting enough of the heat to be preventing the night side from being freezing completely. The day side might be reaching 100 degrees Celsius or more, but the night side might be staying above the freezing point due to the transport of the heat. This is creating the habitable conditions across the much larger surface area than the twilight zone alone. The ocean itself would be circulating, and it would be being driven by the differences in the temperature and the stress of the wind. The warm water would be flowing from the day side toward the night side. The cold water would be returning in the deep currents. However, the constant illumination on the day side is creating the photochemical challenges. The sunlight is driving the chemical reactions in the atmosphere. On the Earth, these reactions are resetting each night when the sun is going down. The reactive molecules that are being produced during the day are getting destroyed at the night, and it is maintaining the balance. On a tidally locked planet, the day side is never getting a break. The photochemistry is running continuously. This could be destroying the biosignature gases before they are spreading to the night side, or it could be creating the exotic chemistry that is being impossible on the Earth. The night side is presenting the different challenges. With no sunlight, the photosynthesis cannot be occurring there. Any of the life on the night side must be relying on the chemical energy rather than the light. On the Earth, the deep-sea ecosystems that are near the hydrothermal vents are demonstrating that the life can be thriving without the sunlight. The chemosynthetic bacteria are extracting the energy from the hydrogen sulfide and the other chemicals. An entire food chain is existing that is being independent of the photosynthesis. Perhaps the similar ecosystems are covering the night side of this planet, and they are being fed by the chemicals that are upwelling from below. The tidal locking is also affecting the tidal forces themselves. With the planet that is always showing the same face to the star, the tidal bulges are remaining fixed in place. The ocean would be having a permanent high tide on the day side and the night side, with the permanent low tide at the poles. This is creating the standing wave patterns that are unlike anything on the Earth. What if this entire biological interpretation is being wrong? The scientists are not assuming that the biology is the only explanation. They are testing the alternatives. Over the past decade, the multiple research teams have been investigating whether the dimethyl sulfide can be forming without the life. The results are complicating the picture. In 2024, one research team published experiments showing that ultraviolet light can drive reactions between methane and hydrogen sulfide. These reactions produce small amounts of dimethyl sulfide. This is the confirmed experimental data, and it has been being replicated under the controlled conditions. The experiments had been working like this. The researchers had been filling a chamber with the gas mixtures that were being similar to what might be existing on the Hycean planets. There was the hydrogen, the methane, the carbon dioxide, and the hydrogen sulfide in the various ratios. They had been sealing the chamber, and they had been exposing it to the ultraviolet lamps that were mimicking the starlight. Over the days or the weeks, they had been sampling the gas and had been analyzing its composition by using the mass spectrometry. The results had been showing the formation of the several organic sulfur compounds, including the trace amounts of the dimethyl sulfide. The mechanism is involving the free radicals, which are the molecular fragments with the unpaired electrons. The ultraviolet light is breaking apart the methane, and it is creating the methyl radicals. These radicals can then be reacting with the hydrogen sulfide, which is also being breaking apart under the UV light. Through a series of the reactions, the methyl radicals are combining with the sulfur to be forming the dimethyl sulfide. The chemistry is complex, and it is involving the multiple intermediate steps, but it is working. You can be making the dimethyl sulfide without the biology. However, the yields were tiny. The experiments had been producing the dimethyl sulfide at the concentrations that were being measured in the parts per billion. To be reaching the parts per million levels that have been being observed on this ocean world is requiring the yields that are being thousands of the times higher. The researchers had been acknowledging this limitation. They had been suggesting that perhaps the continuous volcanic outgassing of the hydrogen sulfide, which was being combined with the intense photochemistry, might be boosting the production. But even the generous assumptions had been falling short of being explaining the observations. Another of the experiments had been exploring the different pathways. The scientists had been simulating the conditions in the molecular clouds, which are the cold, dense regions of the space where the stars are forming. They had been mixing the simple molecules on the ice grains, and they had been exposing them to the radiation. Under these extreme conditions, they had been creating the various organic compounds, including the dimethyl sulfide. This had been showing that the dimethyl sulfide can be forming in the space before the planets are even existing. The comets and the asteroids might be delivering the dimethyl sulfide to the planetary atmospheres during the impacts. But the delivery by the comets is facing the problems. Any of the dimethyl sulfide that was being delivered from the space would be being destroyed quickly by the atmospheric chemistry. To be maintaining the observed concentrations is requiring the continuous replenishment. A planet would be needing the constant bombardment by the dimethyl sulfide-rich comets. We are seeing no evidence for such a bombardment. The crater counts on the planets, and the moons are providing the clues about the impact rates. This ocean world, which is being based on its age and its orbit, should not be experiencing the heavy bombardment. There is another problem: the impact speeds. When a comet is hitting a planet, the velocities are ranging from the tens to the hundreds of the kilometers per second. These hypervelocity impacts are releasing the enormous energy. The temperatures at the impact sites are reaching the thousands of the degrees. Most of the molecules are getting destroyed. The complex organic molecules, like the dimethyl sulfide, would be breaking apart into the simpler fragments. Only the most robust of the molecules are surviving. The dimethyl sulfide is not particularly robust. It should be being destroyed and not being delivered intact. Some of the impacts are occurring at the lower velocities. If the planet is capturing a comet gravitationally, and the comet is spiraling inward slowly, then it might be hitting at just a few of the kilometers per second. These gentle impacts might be preserving the molecules better, but the gentle impacts are rare. Most of the comets are either missing entirely or are hitting hard. The probability of being sustaining the continuous gentle impacts over the millions of the years is seeming to be vanishingly small. There is one of the scenarios where the cometary delivery might be working. If the planet formed in a region rich in cometary material and captured large amounts during its formation, that material could still be stored in its interior. It might slowly release gases over time, shaping the planet's atmosphere. Over the time, the volcanic activity or the convection might be bringing this material to the surface, and it might be releasing the ancient cometary volatiles into the atmosphere. This would not be requiring the ongoing impacts, and it would just be the release of the primordial material. But this scenario is requiring the dimethyl sulfide to be surviving inside of the planet for the billions of the years. The interiors of the planets are reaching the temperatures of the thousands of the degrees. The pressures are exceeding the millions of the atmospheres. Most of the molecules are breaking down under such conditions. Only the most chemically stable of the compounds are surviving. The dimethyl sulfide would almost certainly be being destroyed during the storage. The water is surviving because it is extremely stable. The simple gases, like the hydrogen, the methane, and the carbon dioxide, are surviving. The complex organic sulfur compounds are not. The connection with the comets is remaining a cautionary tale rather than a real alternative. It is reminding the scientists that the biosignature molecules can be having the non-biological sources. It is forcing the more careful interpretation of the observations, but it is not explaining the specific case of this ocean world. The concentrations of the dimethyl sulfide are too high. The lack of the other cometary signatures is too complete. The chemical environment is too destructive to be preserving the delivered molecules for a long term. What about the volcanic sources that are mimicking the chemistry of the life? The volcanoes on the Earth are spewing the sulfur in many of the forms. The sulfur dioxide is dominating the volcanic emissions, and it is being released when the magma is rising and the pressure is dropping. The hydrogen sulfide is following, and it is the smell of the rotten eggs that is being associated with the volcanic regions. The chemistry of the sulfur is complex, and it is having the multiple oxidation states that are allowing it to be bonding with almost anything. In the volcanic environments, the sulfur is reacting with the carbon, the hydrogen, and the oxygen to be forming the dozens of the different compounds. This is the well-established geochemistry, and it has been being observed at the volcanic sites all over the world. Could the volcanic processes on this ocean world be creating the dimethyl sulfide? One of the pathways is involving the methane that is reacting with the sulfur-containing volcanic gases. The methane is abundant in the atmosphere, and it has been being confirmed at a 1% concentration. If the volcanic vents are releasing the hydrogen sulfide, and that hydrogen sulfide is encountering the methane under the right conditions, then the reactions could be producing the organic sulfur compounds. The high temperatures would be favoring the different products than the low temperatures would. The right temperature range might be favoring the formation of the dimethyl sulfide. The laboratory experiments had been exploring this possibility. The researchers had been mixing the methane and the hydrogen sulfide and had been heating them to the various temperatures. At 500 to 700 degrees Celsius, the various organic sulfur compounds had been forming. The carbon disulfide had been appearing. The carbonyl sulfide had been appearing. The methyl mercaptan had been appearing. The dimethyl sulfide had been appearing, but it had been doing so only in the trace amounts. The product distribution was messy, and it was producing many of the molecules simultaneously. That is typical of the abiotic chemistry. The life is producing the specific molecules efficiently. The abiotic processes are producing everything at once, and they are doing so inefficiently. The volcanic pathway is facing the quantitative problems. To be maintaining 10 parts per million of the dimethyl sulfide in the atmosphere is requiring the continuous production that is matching the destruction rates. The scientists had been calculating the necessary volcanic outgassing rates. They had been estimating that the emissions of the hydrogen sulfide would be needing to be exceeding the entire volcanic output of the Earth by the factors of the hundreds or the thousands. This ocean world would be needing to be being one of the most volcanically active of the bodies in the known universe. While it is not being impossible, it is seeming to be unlikely. There is also the problem with the methane. The methane itself is requiring the explanation. On the Earth, most of the atmospheric methane is coming from the biology, and it is being produced by the methanogenic bacteria or is being released during the decomposition of the organic matter. Some of it is coming from the geological sources like the serpentinization, where the water is reacting with the certain rocks to be producing the hydrogen and the methane. but these geological sources are producing the relatively small amounts. The 1% of the methane on this ocean world is exceeding what the abiotic processes are typically generating. If the volcanoes are producing the methane, then they must also be producing the dimethyl sulfide through the same processes. That is creating a self-consistent abiotic scenario, but it is requiring the extraordinarily active volcanism and the specific chemical conditions that are maximizing the production of the organic molecules. The models are struggling to be achieving both of these requirements simultaneously. Either the volcanism is too weak to be producing enough of the gas, or the temperatures are too high to be allowing the organic molecules to be surviving. Another of the volcanic pathways is involving the intermediate water chemistry. The volcanic gases are dissolving in the ocean water. The dissolved gases are then reacting with each other in the solution rather than in the atmosphere. The aqueous chemistry is allowing for the different reaction pathways. Some of the reactions that are not working in the gas phase are proceeding efficiently in the water. Perhaps the dissolved hydrogen sulfide and the dissolved organic molecules are combining to be forming the dimethyl sulfide in the ocean. The dimethyl sulfide is then evaporating into the atmosphere. This aqueous pathway is facing its own challenges. The ocean chemistry is being buffered by the dissolved minerals. The seawater on the Earth is having a pH of around 8, and it is being slightly alkaline. This pH range is strongly affecting what of the reactions are occurring. The formation of the dimethyl sulfide is generally favoring the acidic or the neutral conditions, and not the alkaline ones. But we are not knowing the pH of the water of this ocean world. If the volcanic activity is acidifying the ocean, then that might be favoring the formation of the dimethyl sulfide. However, the acidic oceans would be dissolving the carbonate minerals, and they would be showing the different atmospheric carbon dioxide levels. The observations are not clearly supporting the extreme pH. The truth is that the scientists have not yet been finding a volcanic pathway that is fully explaining the observations without being invoking the extraordinary conditions. The volcanic sources might be contributing some of the dimethyl sulfide. They might be explaining a part of the signal, but explaining the full observed concentration is requiring either the extreme volcanism or the highly specific chemistry, or both. As the explanations are going, the biology is remaining simpler. What if the star itself is making this planet uninhabitable? The red dwarf stars are violent. They are erupting with the massive flares, and they are releasing the energy that is being equivalent to the billions of the nuclear bombs. These stellar flares are blasting the nearby planets with the X-rays, the ultraviolet radiation, and the streams of the charged particles. The flares are happening frequently, and they are sometimes doing so multiple times per day during the active periods. This has been being confirmed through the observations of the thousands of the red dwarfs. We have been watching them be flaring. We have been measuring the energy. The danger is real. Why are the red dwarfs flaring so much? The answer is lying in how they are generating the magnetic fields. The stars are creating the magnetic fields through the dynamo processes, where the flowing electrically conductive plasma is generating the electric currents that are producing the magnetic fields. On our own sun, the dynamo is operating in a shell that is near the surface. On the red dwarfs, the dynamo is operating throughout the entire star because they are being fully convective. The hot plasma from the core is rising to the surface. The cool plasma from the surface is sinking to the core. This is creating the powerful tangled magnetic fields. These magnetic fields are storing the enormous energy. Sometimes the field lines are becoming twisted and are being stressed. When they are releasing that stored energy, then suddenly you are getting a flare. The material that has been being heated to the millions of the degrees is erupting from the surface of the star. The radiation across the entire electromagnetic spectrum is flooding outward. For a planet that is orbiting close by, this is being catastrophic. The radiation is hitting in the minutes. There is no warning, and there is no time to be taking the shelter. What is this radiation doing to the atmospheres? The ultraviolet light, and the X-rays are slamming into the upper atmosphere, and they are ionizing the molecules and the atoms. The ionization is stripping the electrons from the atoms, and it is creating the charged particles. These charged particles are reactive. They are tearing apart the molecules. The complex organic molecules are getting destroyed. On the Earth, our magnetic field and our thick atmosphere are protecting us from the solar flares. Mars is lacking a strong magnetic field and is having a thin atmosphere, and it is doing so partly because the solar wind had been stripping it away over the billions of the years. This ocean world is orbiting much closer to its star than Mars is orbiting our own Sunday. The flares are hitting harder, the radiation is more intense. If the planet is lacking a magnetic field, then the atmosphere is being exposed directly. The scientists are estimating that over the billions of the years, a red dwarf could be stripping away several of the Earth masses of the atmosphere from a nearby planet. The fact that this ocean world is retaining its atmosphere suggests one of several possibilities. It may have a magnetic field gravity strong enough to hold onto the atmosphere, despite losses, or a star that is less active than typical red dwarfs. The magnetic fields are depending on the interiors of the planets. The Earth is having a magnetic field because its liquid iron core is convecting, and it is creating a dynamo that is similar to the stellar dynamos. The rocky planets with the solidified cores are losing their magnetic fields. This ocean world is being massive enough that it might be retaining the internal heat from its formation. If it is having a liquid metallic core, then it could be generating a magnetic field, but no observations are directly confirming this. We cannot be measuring the magnetic fields on such distant planets yet. We can only be inferring their presence or their absence from the indirect evidence. Even if a magnetic field is existing, the flares are still posing the problems for the life. The radiation might not be stripping the atmosphere entirely, but it is penetrating deep enough to be affecting the surface conditions. On the Earth, the ozone layer is absorbing the harmful UV radiation. The oxygen in the atmosphere is creating the ozone. This ocean world is having the minimal oxygen. Without the ozone, the UV radiation is reaching the surface unimpeded. The organisms there would be needing the protection mechanisms, like the thick cell walls, the radiation-resistant proteins, or simply being living underwater, where the water is absorbing the radiation. The frequency of the flares is mattering. If the flares are happening daily, then the life must be coping with the constant bombardment. If the flares are happening yearly, then there are the long recovery periods. The observations of this particular red dwarf are showing that it is relatively old at 2.4 billion years. The old red dwarfs are tending to be being calmer than the young ones. The stellar activity is declining over the time as the stars are spinning down and the magnetic fields are weakening. Perhaps this star has been mellowing enough that its flares are no longer being threatening the planetary atmospheres severely. But even the quiet red dwarfs are flaring occasionally. One of the massive flares could be temporarily destroying the biosignature gases in the atmosphere. If the dimethyl sulfide is getting obliterated during a flare, then the observations that are afterward would be showing the lower concentrations. The multiple observations that were being spread across the months would be revealing whether the concentrations are varying with the stellar activity. So far, the data is coming from just 2 of the observation windows. More of the observations might be showing the temporal variations that are revealing the impacts of the flares. What about the gentler but the persistent stellar wind? All of the stars are emitting the stellar wind, which are the streams of the charged particles that are flowing outward. Our own sun is producing the solar wind that is traveling at about 1 million of the miles per hour. This wind is carrying away the mass. Over the lifetime of the sun, it has been losing a tiny fraction of its total mass through this process. The wind is also carrying the magnetic field lines that are interacting with the planetary magnetic fields. The magnetosphere of the Earth is deflecting most of the solar wind around us. The particles that are penetrating are creating the auroras at the poles. This is the well-understood space physics and it has been being confirmed by the decades of the spacecraft measurements. The red dwarf stars are emitting the weaker stellar winds than our own Sun is by the total mass loss, but their planets are orbiting so close that the density of the wind is becoming important. Imagine being standing in a gentle breeze versus being standing in that same breeze while you are being pressed against the fan that is producing it. This ocean world is sitting 13 million miles from its star. The Earth is sitting 93 million miles from our own Sunday. The planet is orbiting 7 times closer relative to the size of the star. At that distance, the density of the stellar wind is significantly higher. The stellar wind is eroding the atmospheres through the several mechanisms. First, the momentum transfer. The fast-moving particles are colliding with the atmospheric atoms and the molecules. Sometimes, these collisions are imparting enough of the energy for the atmospheric particles to be escaping the gravity. This is what is called the sputtering. One by one, the atoms are getting knocked into the space. Over the millions of the years, the sputtering is removing the substantial atmospheric mass. Second, the charge exchange. The stellar wind is consisting of the ionized particles, and it is mostly being the protons. When these ions are encountering the neutral atoms in an atmosphere, then they can be stealing the electrons. The newly ionized atmospheric atoms are responding to the magnetic fields. They are getting swept up by the stellar wind and are being carried away. This process is being particularly efficient at removing the hydrogen and the helium, which are light and are easily ionized. Third, the atmospheric heating. The stellar wind is depositing the energy into the upper atmosphere. The atmosphere is heating up. The hot atmospheric particles are moving faster. Some of them are reaching the escape velocity and are drifting away. This thermal escape mechanism is being most effective for the light elements. The hydrogen is escaping the fastest. Then it is the helium. The heavier elements like the nitrogen, the oxygen, and the carbon are escaping more slowly, but they are still escaping. Mars is providing a cautionary tale. Mars had once been having a thicker atmosphere, and this is being evident from the ancient river valleys and the lake beds. Over the billions of the years, the solar wind had been stripping most of it away. Mars had been losing its magnetic field early in its history when its core had been solidifying. Without the magnetic protection, the atmosphere was being vulnerable. Today, Mars is having less than 1% of the atmospheric pressure of the Earth. The planet had been drying out and had been freezing. This has been being confirmed by the rover missions and the orbiting spacecraft that had been measuring the rates of the atmospheric loss directly. Could the same fate be befalling this ocean world? The hydrogen atmosphere might actually be helping to be protecting against the loss. The hydrogen is the lightest of the elements. It is occupying the uppermost of the atmospheric layers. The stellar wind is interacting primarily with this hydrogen, and it is stripping it away, but it is leaving the heavier molecules that are deeper in the atmosphere untouched. The massive hydrogen envelope is acting as a sacrificial shield. As long as the planet is replenishing the hydrogen from below, then it can be maintaining the atmosphere indefinitely. But where is the replacement hydrogen coming from? If the planet is having a hydrogen-rich interior, then the convection and the outgassing could be releasing the hydrogen continuously. Alternatively, if the planet is containing the water, then that water could be breaking down into the hydrogen and the oxygen. The hydrogen is escaping. The oxygen is reacting with the surface materials or is getting incorporated into the molecules. This would be slowly drying out the planet over the billions of the years. Venus is demonstrating this process. Venus had been losing an ocean's worth of the water through the escape of the hydrogen. The planet had been baking dry under a runaway greenhouse effect. The scientists are estimating the rates of the atmospheric loss by using the models that are inputting the properties of the stellar wind, the gravity of the planet, the strength of the magnetic field, if any, and the atmospheric composition. For this ocean world, the estimates are varying widely, and they are depending on the assumptions. The optimistic models are suggesting the rates of the atmospheric loss that are low enough that the planet is retaining the atmosphere for the billions of the years. The pessimistic models are suggesting the rapid loss that would be stripping the atmosphere within the hundreds of the millions of the years. The fact that the atmosphere is remaining after 2 billion years is providing a constraint. The loss rates cannot be being as high as the pessimistic models are predicting. But beyond that, the conclusion is remaining uncertain. What about the crazy elliptical orbit? Remember that the elliptical orbit with an eccentricity of 0.09 is meaning that the distance of the planet from its star is varying by 12% between the closest and farthest approach. That is translating to a 43% variation in the received starlight. Imagine if the seasons of the Earth were to be working that way. Instead of the gentle changes in the temperature that are being driven by the axial tilt, we would be experiencing the violent swings every few months. This has been being confirmed by the orbital mechanics, and it has been being calculated directly from the precise timing measurements of the transits. The orbital period is 33 days. That is meaning that the planet is going from the maximum of the starlight to the minimum of the starlight in about 16 days, and then it is going back to the maximum in another 16 days. For the life, this is creating a punishing rhythm. Just as the organisms are adapting to the high temperatures and the high levels of the light, the conditions are reversing and the temperatures are dropping and the light is dimming. Then, before the adaptation is being completing, the conditions are reversing again. It is like trying to be acclimating to the summer and the winter simultaneously. On the Earth, the seasonal changes are happening slowly enough that the life is adapting. The trees are sensing the changes in the day length months before the winter is arriving, and they are preparing by moving the nutrients and shedding their leaves. The animals are building up the fat reserves or are migrating to the warmer climates. These adaptations are working because the seasons are lasting for the months and are repeating predictably every single year. But the 33-day cycles are faster than most of the biological adaptations. A tree cannot be growing the leaves and then be shedding them and then be growing them again every few weeks. The microbial life might be handling this better than the complex organisms. The bacteria are reproducing quickly. The generation times can be being the hours to the days. In 33 days, the bacteria are going through the dozens or the hundreds of the generations. That is allowing for the rapid evolution. The bacterial populations could be adapting to the changing conditions through the natural selection, and it would be operating in real time. The beneficial mutations could be spreading through the population within one single orbital period. The complex organisms with the generation times of the years cannot be adapting this quickly. The temperature swings are affecting the ocean circulation. The warmer water is expanding, the cooler water is contracting. As the planet is moving through its orbit, the ocean is literally swelling and is shrinking. This is creating the tides that are being separate from the gravitational tides. These thermal tides would be driving the currents and they would be mixing the surface and the deep water. The mixing might help distribute nutrients and benefit marine life. But it could also disrupt stable water layers and harm organisms adapted to specific depths. The atmospheric chemistry is changing with the temperature too. The rates of the chemical reactions are doubling every 10 degrees Celsius as a rough rule. If the surface temperatures are varying by 20 degrees over the orbital cycle, then the reaction rates are varying by a factor of 4. The destruction of the dimethyl sulfide is happening 4 times faster at the closest orbital approach than it is at the farthest approach. The production rates are also varying if they are depending on the temperature-sensitive biological processes. The result is that the atmospheric concentrations might be oscillating with the orbit. The observations from the Webb telescope had been capturing the snapshots at the specific moments during the orbit. The data is representing whatever of the conditions had been existing when the planet had been happening to be transiting its star. If the concentrations are varying significantly, then the different observations might be showing the different levels of the dimethyl sulfide. Comparing the multiple observations could be revealing whether the concentrations are being stable or being variable. So far, the two observations are showing the consistent results, but the two data points are not being enough to be ruling out the variability. The elliptical orbit is also affecting the concept of the habitable zone. Traditionally, the habitable zone is being defined as a distance range, where a planet with the Earth-like atmosphere is maintaining the liquid water. That is assuming the circular orbits. For the elliptical orbits, the planet is spending a part of each of the orbits inside of the traditional habitable zone and a part of it on the outside. This ocean world is swinging from just inside to just outside of the habitable zone with each of its orbits. Whether the liquid water can be persisting under such conditions is depending on how quickly the ocean is responding to the changing conditions. The high heat capacity of the water is providing the buffering. The oceans are not heating up or are cooling down instantly. They are lagging behind the atmospheric changes. Even if the air temperatures are swinging dramatically, the ocean's surface temperatures might be varying by just a few of the degrees. The deep ocean temperatures might be barely changing at all. The life could be existing in these more stable, deep layers, and it could be being protected from the orbital variations. Alternatively, the life could be migrating vertically, and it could be following the optimal temperature layers as they are moving up and down. What must the future observations be confirming to be settling the debate? The next of the observations must be separating the dimethyl sulfide from the dimethyl disulfide. The current data is showing the absorption features that are being consistent with either of the molecules or both. They are the chemical cousins with the similar spectral signatures in the observed wavelength range, but they are not being identical. Expanding the observations to the longer wavelengths would be revealing the differences. The dimethyl disulfide is having the strong absorption features that are between 6 and 7 microns. The dimethyl sulfide is not. Observing at those wavelengths would be determining which of the molecules is being present. This is mattering because the dimethyl sulfide and the dimethyl disulfide are forming through the slightly different pathways on the Earth. The dimethyl sulfide is coming primarily from the phytoplankton that are breaking down the dimethyl sulfonneopropionate. The dimethyl disulfide is coming primarily from the bacterial metabolism. Finding one versus the other versus both would be constraining what of the types of the organisms might be existing. All are being the biosignatures, but they are telling the different stories about the ecosystem. The observations must also be increasing the statistical significance. The current confidence is sitting at 3 sigma, which is 99.7%. That is meaning a 0.3% chance of the error. The science is demanding the 5 sigma for the discovery, which is dropping the probability of the error to 0.00006%. Achieving the 5 sigma is requiring more of the observation time. Each of the additional transit observations is improving the signal-to-noise ratio. With 2 or 3 more of the transits, the scientists are estimating that they would be reaching the 5 sigma. The 5 sigma is not being arbitrary. It is the threshold where the chance is becoming so unlikely that the systematic errors are becoming the main concern. At the 3 sigma, you might be seeing a pattern by the luck. At the 5 sigma, the luck is essentially being ruled out. Any of the remaining uncertainty is involving whether the instruments are being calibrated correctly or whether the models are being complete. Those questions can be being addressed through the independent verification and the alternative analysis methods. The independent verification is meaning that the other teams are analyzing the same data. The scientific results are gaining the credibility when the multiple groups are reaching the same conclusion by using the different analysis techniques. The data from the Webb telescope is being public after a short proprietary period. Anyone can be downloading it and be analyzing it. The multiple teams have already been looking at the signal of the dimethyl sulfide. They are generally agreeing that it is real, though the debates are continuing about the interpretation. More of the data would be giving more to be analyzing, and it would be helping to be resolving the disagreements. The observations should also be searching for the other biosignature candidates. The methyl chloride is being predicted to be being a biosignature on the Hycean worlds. It is forming when the organisms are incorporating the chlorine into the organic molecules. The oceans of the Earth are containing the methyl chloride that has been being produced by the marine algae and the kelp. Finding it on this ocean world would be providing the independent evidence for the biology. Conversely, not finding it might be suggesting that the abiotic processes are dominating. The oxygen is remaining the gold standard of the biosignatures on the Earth. The photosynthetic organisms are producing the oxygen as the waste. It is accumulating in the atmosphere because the constant replenishment is overcoming the chemical destruction. Finding the oxygen on an exoplanet would be being the powerful evidence for the life. Though the abiotic oxygen production is being possible through the photolysis of the water, this ocean world is showing no oxygen, which is actually fitting the Hycean hypothesis. The hydrogen atmospheres would not be accumulating the oxygen, even if the organisms were to be producing it. The hydrogen would be reacting with the oxygen immediately. The seasonal variations are deserving the attention. If the concentrations of the biosignatures are changing over the time, then that might be reflecting the biological cycles, the orbital variations, or the effects of the stellar activity. The atmosphere of the Earth is showing the seasonal cycles in the carbon dioxide as the plants are growing and are decaying. The similar cycles on another world would be suggesting that the biology is responding to the environmental changes. Alternatively, the stable concentrations over the months or the years might be suggesting a robust equilibrium between the production and the destruction. The ultimate goal is not just being confirming the presence of the dimethyl sulfide, but being understanding its source. That is requiring being detecting a suite of the molecules that together are pointing unmistakably to the biology or are clearly indicating the abiotic processes. No single molecule is proving that the life is existing, but the combinations of the molecules that are only making the sense together with the biological production would be being compelling. What of the threshold must we be crossing before we are declaring that we have been finding the alien life? The stakes could not be being higher. Announcing the discovery of the alien life would be being one of the most profound of the moments in the human history. It would be answering a question that we have been asking for the thousands of the years. Are we being alone? The answer would be reshaping the philosophy, the religion, the science, and our sense of the place in the entire universe. Getting it wrong would be being catastrophic. Claiming that the life is existing when it is not would be destroying the credibility. The future of the genuine discoveries might be being doubted. That is why the scientists are demanding the 5 sigma certainty. The 5 sigma is meaning that the probability of being wrong through the random chance is less than 1 in 3.5 million. That is like flipping a coin and be getting the heads 22 times in a row. It is being possible, but it is being so unlikely that you would be betting everything that the coin is being rigged. In the particle physics, the 5 sigma is how the scientists had been confirming the Higgs boson. In the astronomy, the 5 sigma is how the gravitational waves had been being announced. For the alien life, anything less would be being irresponsible. This is not being the official policy, but it is rather being the scientific consensus that has been being built through the hard experience. The history is teaching the caution. In 1996, the scientists of NASA had been announcing the possible fossilized bacteria in a Martian meteorite. The news had been making the headlines all over the world, but the further analysis had been revealing the alternative explanations. What had been looking like the bacterial fossils might be being the mineral formations. What had been looking like the biological markers might be being the contamination. Today, most of the scientists are considering the evidence to be being insufficient. The episode had been teaching everyone who had been being involved to be demanding the stronger proof before making the bold claims. More recently, the phosphine on Venus had been generating the excitement. In 2020, the scientists had been reporting detecting the phosphine gas in the clouds of Venus. On the Earth, the phosphine is being produced by the bacteria or the industrial processes. Finding it on Venus had been suggesting the possible microbial life that was floating in the clouds. But the reanalysis had been questioning the detection. The spectral signature might actually be the sulfur dioxide that had been misidentified. The claimed phosphine might not be existing at all. The confidence had been eroding from the strong detection to the uncertain. Maybe those false starts had been having the consequences. The public interest in the astrobiology is remaining high, but the skepticism had been increasing. The media outlets are treating the new claims more cautiously. The scientists are facing the pressure to be absolutely certain before going public. The discovery of the dimethyl sulfide is coming with those lessons that have been learned. The research team is repeatedly emphasizing the caution. They are not claiming that the life has been found. They are claiming a biosignature that is requiring the explanation. The difference is mattering. A biosignature is a signal that is consistent with the life. It is not the proof of the life. The other of the explanations might be existing. The signal might be misinterpreted. The observations might be containing the errors. Only after exhausting the alternatives and confirming the signal repeatedly can the scientists be considering claiming the discovery. That process is taking the time. It is requiring the patience. It is requiring the additional observations that might be taking the years to be obtaining. The public communication is challenging this approach. The moment that the preliminary results are suggesting the alien life, the media coverage is exploding. The headlines are simplifying the complex findings. The nuance is getting lost. The public is hearing that the scientists had been finding the aliens when the scientists had actually been saying that they had been finding a signal that might be indicating the life. Managing the expectations is becoming crucial. Overclaiming is causing the backlash. Underclaiming is meaning that the discoveries are getting ignored. Finding the balance is difficult. Some are arguing that the 5 sigma is too strict for the biosignatures. Unlike the particle physics where the experiments can be repeated easily, the astronomical observations are depending on the limited telescope time. Waiting for the 5 sigma might be taking the decades. Meanwhile, the signal is real. Should the society be waiting for the perfect certainty before acknowledging the probable discoveries? Others are countering that the premature announcements are causing more of the harm than the delays. It is better to be late and be right than to be early and be wrong. This ocean world is existing at that threshold. The signal is strong. The interpretation is reasonable. The alternative explanations are struggling to be explaining the observations. But the doubt is remaining. Maybe something that is unexpected is happening. Maybe the models are missing the important chemistry. Maybe the multiple coincidences are aligning to be mimicking a biosignature. Reaching the 5 sigma would not be eliminating these possibilities completely, but it would be pushing them into the implausibility. The next year will be crucial. If the additional observations are reaching the 5 sigma, and if the alternative explanations are continuing to be failing, then the scientific community will be facing a decision. At what point is the probable becoming the definite? At what point are we accepting that we have been detecting the life beyond the Earth? That decision will not be being made by one person or one team. It will be emerging from the consensus across the entire field of the astrobiology. We are standing at the very edge of the knowing. 124 light-years away, a planet is orbiting a dim red star. Something in its atmosphere is creating the chemicals that on the Earth are only being produced by the life. Something is happening there that we cannot yet be explaining without invoking the biology. The telescope is staring. The observations are accumulating. The certainty is building. Within the months or the years, we will be knowing whether this ocean world is being inhabited or whether we had been fooling ourselves again. Either way, we have been entering a new era. The era where finding the life elsewhere is not a fantasy, but a scientific question with the real data and the real answers that are approaching. The question that has been haunting the humanity since we had first been looking at the stars may finally be being answered. We are close, so very close,